caso più grave, dai.
No, no. Good morning, everybody. Please take your seat. We have in line Giorgio Parisi to give the welcome of Accademia dei Lincei. I can give it myself, welcome. And ce l'abbiamo?
Sì, sto qua.
Oh, eccolo qua, ok.
Okay, so thank you very much, Luciano. I'm very happy to give the welcome to everybody here on behalf of the Accademia Lincei. I'm a vice president of the Accademia, and I would like to thank both the organizer committee, the speaker, and all the people that are present here, because this is a very important meeting. The Laboratory Nazionale del Gran Sasso is a really incredible scientific endeavor, which has been possible by dedicated effort we started more or less 40 years ago. And they are an incredible laboratory to do cosmic ray studies, neutrino studies. I mean, it's one of, or maybe the place with less radioactivity induced by cosmic rays in the world. And the physics that have been done in this nearly 40 years, maybe 35 years of work is something incredible. And there have been a lot of studies on many properties. For example, one of the things that I remember among the others was, for example, the beam that were of neutrino beam sent from CERN to Gran Sasso. That was very important. There were many other achievements, and the Laboratory Nazionale Gran Sasso has been a wonderful place to study solar neutrinos. Solar neutrinos are extremely important for many things, both for neutrino oscillation to understand the physics on the sun and so on. And so the results are really magnificent, and this result have been magnificent not for many reasons. First, all of the support that was done to Laboratorio Nazionale Gran Sasso by the many presidents, starting from Nino Zigighi, Nicola Cabibbo, Luciano Mariani, and all other presidents up to the nowadays president Zoccoli, that are given for the wonderful directors that have been there in the past and at the present. So it's a wonderful idea to organize this meeting. I'm very happy on behalf of Academy also that this meeting was organized in our Academy, where many of the protagonists belong. And so thank you very much to everybody, and goodbye.
Thank you very much. Thank you very much, Giorgio. Now, I have to announce you a small change in the program, because you can believe it, but I forgot home my computer with my slides. I have to leave, and so I had my briefcase, and I took the briefcase but didn't take the so I will have to run home to pick it up back, and we'll come back at the coffee break. And meanwhile, I can give the floor to Till Kirsten, who kindly will do his first, as a first talk, will talk to you about Gallex. So please come here. And also, there is also a delay about Zoccoli. Okay. There is another change in the program, that Professor Zoccoli is unable to come and give you the welcome of INFN, and this will be given by Pallavicini as in his place. So I will give the floor then to Pallavicini, then you give it to Till Kirsten, and I go rapidly to pick up my computer. Thank you very much.
So thank you, Luciano. I bring the message of Antonio, who unfortunately is in another meeting in Elba, and he has to deliver a talk exactly in this moment, so he cannot even give a remote meeting. It is a pleasure to say hello to all people joining here. It's a pleasure to see many old friends met in Gran Sasso along many, many years. The two experiments we are celebrating today are among the most important happened at Gran Sasso in the last 30 years. The lab is a key lab for INFN. We have 4 important national labs, but clearly LNGS play a special role. It's one of the largest underground lab in the world, is one of the first to be fully dedicated to the study of underground physics. And we have here many former presidents of INFN, and each of them had his own hard moments and beautiful moments to support, to make the lab grow, to defend it occasionally from problems occurring recursively there, but has always been a main priority of the lab. We also have many former directors of the lab, so I'm sure everybody understands and remembers the many beautiful moments we had in the last 35 years, but also the difficulty in keeping the lab running and growing. Gallex and Borexino have been two fundamental elements to show that the lab is a top-level scientific lab in the world. As was recalled by Giorgio Parisi, the results were astonishing, in both cases above the expectations. They really measured better and more than what initially envisaged by both experiments. And of course, it is a pleasure to celebrate Gianpaolo and Till and all others, all of us that in different moments and in different roles gave a contribution to the lab and to the science and to the physics. And of course, to the INFN institutions represented here by myself, but also by the former presidents and director who along the 35 years worked on this. So I don't want absolutely to take too much time on this. As Luciano said, we have a switch. So it is a pleasure to ask Till Kirsten to join the stage and start his speech. Thank you very much.
Welcome to this meeting. Of course, Gianpaolo and myself, we are very pleased that somebody remembers us. And I will give you my talk. Dear Presidents Parisi, Antonelli, and Zoccoli, dear colleagues and friends. The Gallex adventure started in 1984 and culminated with the discovery of solar PP neutrinos in 1992. Subsequently, we corroborated and enlarged the data body during the following 12 years, till 2005. Today, I will talk about the intentions, the performance, and the results. Like any ordinary main sequence star, our sun is a fusion reactor. This was a very solid theory that nobody seriously doubted. On the other hand, till 1992, there was no direct experimental evidence for proof for this, since nobody actually could see in the core of the sun. And in good science, it is tradition that if I believe a theory, I have to have some experimental evidence. And in principle, you couldn't look in the core. So according to the standard solar model, in the core of the sun produces energy by converting hydrogen in helium via a network of interactions. Thereby, also various kinds of neutrinos are generated. Other than the bulk of the produced energy, which takes longer, much longer, the neutrinos escape the core instantaneously since they undergo weak interactions only. Hence, at Earth, 8 minutes after creation in the solar core, neutrinos constitute a quasi-real-time signal of what is going on now in the center of our star, provided we can detect them. But now, when they so easily penetrate 700,000 kilometers of dense matter, how can one recognize or catch them in a terrestrial detector with dimensions certainly less than 100 meters or so? One way is to collect the products of neutrino interactions with the target atoms over a rather long time period, order of months or year, 1 year or so, for integral determination afterwards. Radiochemistry is used to extract the radioactive reaction products at the end of the exposure time. The other thing is you need, of course, very large detectors. Dimensions are required to compensate for the low interaction cross-sections.
If you want to change the slide, you have
Oh,
to
yeah,
do it.
yeah, I'm sorry. Yeah, this is what it is. So, let me have my pointer. Oh, okay.
Why you're not using that one?
I want to use the pointer.
Okay.
Oh, yeah. So you see these reactions. There is the first initial reaction is that two protons interact to form deuterium. In this way, we produce electron neutrinos of very low energy. There is another chain which gives you the pp2 cycle, which gives you beryllium-7, and the neutrinos emitted in this branch are intermediate in energy. And the third one is the boron-8 neutrinos, which come from this reaction where a proton reacts with beryllium-7 and forms boron-8. And so the expected neutrino fluxes by the standard solar models, they arrive are for PP neutrinos about 60 billion per square centimeter on second. For beryllium-7 neutrinos, about a tenth of that. And for boron-8 neutrinos, very, very little. Just, you see, a factor of 10 to the 4 below PP flux. But in terms of predictability, the PP neutrinos have a very big advantage. And that is, you don't need to know a specific solar model to predict them. You can just measure the solar luminosity as a whole, and you know the expected PP flux because it's 93% of the signal. Whereas the boron-8 neutrinos, they are easier to detect because they are higher in energy, but they don't get the PP neutrinos because their energy threshold is above. So one requirement for such experiments is to go deep underground. And sophisticated low-level techniques are required for the activity measurement and for background discrimination. To judge the feasibility of a proposed detector, reliable theoretical estimates for the expected neutrino fluxes are a prerequisite. The standard solar model goes back to Eddington, Critchfield, van Weizsäcker, and Bethe. After 1960, the exact quantification occurred through the tedious efforts of John Bacall. Here, I only use the resulting spectrum, and you see the PP flux is very dominant. I have a problem with the laser pointer. Now I have you see PP is 10 to the 11 here on this scale. Boron-8 is 10 to the 6, and beryllium-7 is 2 line sources at intermediate energies. So these are not so well predictable as the PP neutrinos because any student can just divide the solar luminosity through the energy output of 26 MeV, and he knows how many PP neutrinos to expect. One could summarize the situation with a joke. If the PP neutrinos are the cake, the boron-8 neutrinos are the smell of the cake. Now, okay, so the first considerations for actually detecting solar neutrinos go back to Bruno Pontecorvo as early as 1946. He proposed solar neutrino detection through inverse beta decay on chlorine-37, leading to radioactive argon-37. The first practical feasibility studies for a chlorine experiment was done by Raymond Davis at Brookhaven National Laboratory. And he started at the Homestake Gold Mine in South Dakota in 1967. At this time, 1967, I was a postdoc at Brookhaven and became fascinated by Davis' project and his personality. We stayed in a very friendly relationship ever since. Davis was the first to demonstrate that it is possible, because the people were very skeptic about some chemists mixing around with elementar particles. He was the first who should demonstrate that it is possible to detect a few atoms out of hundreds of tons of target material and to count the subsequent decay of the neutrino-produced radioactive argon-37 atoms. The half-life of argon-37 is 35 days. this is sufficiently long to accumulate production over some months of exposure, yet it is sufficiently short to have a reasonable specific activity for detection afterwards. Now, the solar neutrino problem developed from the result of Davis' first experiment. The signal in this pioneering home-stake experiment is only about 1/3 of what was expected from the standard solar model, mainly for boronate neutrinos. This established the solar neutrino problem. And there were two principal avenues to account for this factor 3. Either by deviation due to an incomplete or false description of the solar interior in the solar in the standard solar model, and or by inaccurate input parameters for this calculation. The second and opposite solution is the so-called particle physics solution. That is, that the deficit is due to non-standard neutrino properties, such as, for instance, non-zero neutrino mass at the root of neutrino flavor oscillations. Later today, Alex Smirnov will tell us about the quantitative consequences of neutrino oscillations for the expected experimental rates and all types of solar neutrinos. To explain this idea of neutrino oscillations is just a cartoon here which shows that between Sun and Earth something happens on the way, 150 million kilometers, and if the oscillation length of this effect which we are talking about is in between, then you have a sensitivity for the mass square of the neutrinos which are required to explain the oscillations of the order of as small as 10 to the minus 11 e-volt over c square. Now, later today, Alexei Smirnov will tell us about the quantitative consequences of neutrino oscillations for the expected experimental rates in all types of solar neutrino experiments. From the results of the chlorine experiment alone, it is impossible to distinguish whether the deficit observed in the chlorine experiment is due to details of the solar model or to neutrino oscillations. For this distinction, it is necessary to choose a reaction that is sensitive to PP neutrinos, the majority, far majority, because the PP flux at origin does not depend on specific solar models. This demands a detection reaction with very low threshold. If you study the nuclide chart, the only practical option for this is to use gallium. In 1965, Viktor Kuzmin from the Lebedev Institute proposed plans for a gallium experiment in the Caucasus-Baksan Valley underground laboratory of the Russian Academy of Science. But the practical implementation there was far away from becoming real. Now, the radiochemical method is based on, in this case, based on gallium-71. And there was a meeting in Brookhaven and Heidelberg. We studied in close contact the feasibility of an eventual gallium solar neutrino experiment. And in March 1979, we defined the technical, fiscal, and practical possibilities in the first BNL-MPI Heidelberg Solar Neutrino Coordination Meeting and agreed to go ahead for an experiment in the home stake mine in with gallium in form of aqueous gallium chloride solution. This is a picture from this, I would say, historical meeting where Heidelberg and Brookhaven agreed. Ray Davis, Gerhard Friedlander, John Bacall, Maurice Goldhaber, Israel Ostrovsky, Keith Rowley, Jerry Udis, that's myself, and that is Ken Lundy. It was decided that BNL, Ray Davis, Israel Ostrovsky, Keith Rowley, should be mainly responsible for the radiochemical part of, while MPR Heidelberg, Wolfgang Hambel, Gerd Kirsten, Till Kirsten and Gerd Häuser, for the low-level counting of the few product 71 germanium atoms to detect low-level counting was our specialty. However, a major obstacle for the idea was the rarity and expense of gallium. One would require 10 to 100 tons. This was, in this time, 1 world annual production. That's what we needed of gallium. Industry had to give us 1 annual world production of an element, which is used in semiconductor and so on. And so that was clearly a money problem, and gallium funding should be shared by the institutions. Key players in the US in this financial business have been John Bacall, Gerhard Friedlander, and Ken Lundy. In the next years, we made good progress in a pilot experiment at the BNL site. With 1.3 tons at least, it's not little, but it's not nothing. 1.3 tons was $1 million of MPE-funded gallium in form of gallium chloride solution. It was shipped to Brookhaven, and the pilot tank was built up there in the lab. Unfortunately, all these efforts failed because of lacking administrative BNL support, lack of funds, and lack of underground space at home stake, or elsewhere in the US or in Canada. We searched everywhere. We have been at many places to look what's possible, and nothing was there. When this became clear to me in 1983, I considered to perform the gallium experiment in Europe. John Bacall was shocked and told me that DOE would come over with the funds definitely next year, as he promised in all previous years. But I had no choice. I may say, however, that this decision has never disturbed the friendly and fruitful cooperation between Heidelberg and the Brookhaven colleagues during all coming years. Brookhaven's radiochemists, Robert Hahn and Keith Rowley, have been important members of the Gallex collaboration from early on. Always have to change between pointer and transport. So, you see we had a problem. If you want to do something where you need a world annual production of gallium, in the middle of this slide is the dollar sign, you see? So you needed people, institutes, with funding, of course, and an underground laboratory, because only underground was a chance to get rid away of the effects of cosmic rays. So many questions. Could industry achieve the required amount and radio purity of gallium? Would it be possible to develop a functioning germanium-gallium separation technique with separation factor of 10 to the 30? Could one develop a low-level counting procedure for germanium-71 counting? Could one establish a committing international network of top scientists with a respective expertise and support by their agencies? Is there a suitable underground laboratory? Before all these questions are answered, How can you dare to ask somebody for $100 million if you do not even know where to go? Cosmic rays can be shielded by going underground. An overburden of 1,200 meters of rock, as in Gran Sasso, corresponds to a shielding of circa 3,500 meters of water equivalent. The radiochemical purity must be in the range of 10 to the minus 13 to 10 to the minus 16 uranium or thorium gram per target, because the alpha decay series interfere with alpha N and P sequences. They mimic neutrino capture by forming germanium-71, but through other channels. Another background source is NP reactions due to fast neutrons emitted from the rock wall of the fast underground lab. An all-important practical requirement is the feasibility of the chemical separation of the product nuclei from the target separation. Factors of up to 10 to the 30 are needed. Ideal are schemes where the neutrino capture product is volatile and can be flushed out with a gas stream, as it is the case in Gallex with ultra-pure nitrogen, as well as in Homestake, where helium is used to get the argon-37 out. After the product nuclei are successfully separated from the target, they must be counted. The products from inverse beta decay are radioactive by electron capture. The detectable radiation in this process consists of KeV Auger electrons and X-rays. Such weakly ionizing low-energy radiation is normally detected in low-level gas proportional counters, which contain the radioactive species as an admixture to the counting gas. Typical decay rates are of the order less than 1 per day. This calls for counter backgrounds, less than 1 per week. Techniques towards achieving this goal are ultimate low-level procedures, radiochemical purity, counter miniaturization, as well as energy and pulse shape analysis with fast electronics, transient digitizer, and neural network analysis. We did KE 35 years ago. Last but not least, the target material for a radiochemical solar neutrino experiment must be attainable and affordable in sufficient quantity and purity. If one needs an annual volt production of gallium to get industry interested, you must convince them that you are not crazy and that you can pay for it. But how can one ask for this unless you know where to go with your experiment, deep underground being an indispensable prerequisite? All of us are proud that we have succeeded to solve all these puzzles. Essential were both great support of European funding institutions and foundations and the enthusiastic support of the pioneers that got the LNGS underground laboratory going. Nicola Cabibo, Luciano Maiani, and Enrico Bellotti, the first director of LNGS, member and at the same time great supporter of Gallex, especially in the critical initial phase when LNGS was still in statu nascendi. There are the heroes. Now, the course of events that follows is listed here. 1979, underground laboratory ideas were proposed by Antonio Sikiki, president of INFN. 1982, start of excavations. First, I met with Nicola Cabibo in 1984 at a hint from Ettore Fiorini, which was a good friend of and colleague because we worked on double beta decay both. We with the geochemical method and he with the counting method. So in an analogy for double beta decay, it was Borexino and Gallex corresponded to Milano and Heidelberg concerning double beta decay. Now, the great thing, and to my big release, because I was running around in Europe and asking people to get excited. And the key moment was when Nicola decided, yes, we will make space for you. That was the beginning of everything. So that led to the formation of the Gallex formation between 1903 and 1995. And this assurance was given in a letter from the 30th July of 1985 that allocation at LNGS is guaranteed. And that gave me the arguments to get the money somewhere. So through Max Planck, etc. Now, the construction of the Gallex experiment at Gran Sasso was between 1986 and 1991, and the start of solar neutrino recordings was in May 1991. And after 1 year of measurements, we had first really important initial results. And this period was 14 runs, each lasted about a month, called Gallex 1, period Gallex 1. And this is the collaboration which had formed. We had Brookhaven, this is in arbitrary order, Brookhaven, Saclay, MPI Heidelberg, Nice, this was F. Schatzmann as theoretician in astrophysics, Gran Sasso with Enrico Bellotti, Nicola Ferrari, Silvia Pezzoni, Carla Catadori, Helmut Lalla, and Tomo Stolacic. TU München was participating among, I call only the heads of these groups. They were much larger with other people. Franz von Feilitsch, Rudolf Mössbauer, who supported us strongly, and Uli Schanda. Initially the idea was chemistry is Brookhaven stuff and counting is Heidelberg stuff. Now, I left US, that means I left the chemistry. So that was another thing. Who is doing, we were no radiochemists in Heidelberg. Not in that by technical implication sense. And this role, there was a question, but who replaces Brookhaven? I mean, as I said, they participated partially and only after we had started. They sent Keith Rowley, so there was no fight, but they were not the leading role. We needed chemists. And Karlsruhe, Forschungszentrum Karlsruhe with Ebert and Henrich were key persons when the issue was how to arrange these big tanks and do the chemistry there. That is technical chemistry. And that was Karlsruhe, then Milano with Cremonesi, Fiorini, Zanotti, I cannot read all these names, Roma with Silvio D'Angelo, Rita Bernabe. It was a big collaboration. And Israel, the Weizmann Institute was participating with Israel Dostrovsky. So in 1987, after the collaboration was assembled, we organized a collaboration meeting at Gran Sasso, and this was the Gallex collaboration in Nascendi at the time when the big hall was in Nascendi. This is underground in hall A excavation site. This is the view. You see here the big Gallex building in front. The big wing is a crane which allows you to handle and bring 20-ton objects or 50-ton objects, a very heavy crane to go into this exposure building. Test pilot experiments. Yeah, okay, I should simply just say the basic reaction here is this is no. Where are we? No, this is the wrong way. Ah, here we go. Okay. This is the basic reaction here. Gallium-71 captures an electron neutrino, forms germanium-71, threshold very low, 230 keV. Remember, the PP neutrinos have energies up to 420 keV. Gallium-71 isotope in gallium is 40% approximately. And it decays by electron capture with 16.5 mean life. And the question is, how is the signal composed in these model calculations? And it is the following. The PP neutrinos, yes, is now not fluxes, but production rates. And of course, the main substance, there is a unit which is just defined to express in this range of almost nothing the production rates, and that's called SNU, solar neutrino unit. And the prediction was 128 solar neutrino units, 72 from PP, 35 from beryllium-7 neutrinos. And what Davis measured for boron-8 neutrinos, contributes only 10% to the signal in our experiment. This is the definition of one SNU, 1 event per 10 to the 36 target atoms per second. Now, our target was about 100 tons of gallium chloride, acidic solution containing 30 tons of natural gallium, and that means 12 tons of natural gallium-71. The extraction of germanium-71 occurred every 3 to 4 weeks by nitrogen purging of the gallium chloride solution. The reason why we don't use gallium metal, but like the Russians try, gallium chloride solution is because this is chemically speaking, a very well-known aqueous ions chemistry what occurs. And so if you have the gallium formed, germanium formed, it's immediately converted in this medium, is immediately converted in germanium tetrahydride. And this is useful in a proportional counter because, you know, a classical counting gas in proportional counting of low activities is methane, argon-methane mixture. And instead of methane, germane is doing almost the same. So it's a very good copy of okay. And therefore, this is formed in this chemical form. And the detection, the expected signal was now about 9 germanium-70 counts detected per extraction. Thank you. On commercial terms, Ron Poulenc constructed the factory to produce 30 tons of gallium after funding was assured by the Max Planck Society and by the Alfred Krupp von Bohlen und Halbach Foundation. Klaus Ebert and Edmund Henrich from FZK Karlsruhe contributed the large-scale chemical engineering for the germanium-gallium separation under the difficult condition of radiochemical hyperpurity. It was decided to use the target in form of an aqueous solution of 8 molar gallium chloride. In this highly acidic medium, the neutrino produced germanium-71, together developed specific low-level techniques for germanium-71 proportional counting at world record low-level counting, low background rates. The germanium-71 counting gives you 2 peaks, the L peak of the, at 1.2 keV and the K peak at 10.4 keV. Pulse shape analysis distinguishes between genuine fast-rising pulses due to point-like germanium-71 decays and slow pulses of extended ionization tracks from Compton-like background events where the primary ionization in the proportional counter occurs at various radial distance from the anode wire. For background discrimination, we have applied neural network techniques 35 years ago. Typically, we performed 1 run, extraction per month, governed by the favorable mean life of germanium-71 of 16.5 days. The extraction nitrogen purge time was about, after end of exposure, was about 1 day. Each run was counted for about 6 months. In this type of low-rate experiments, few counts per month only. Radiochemical purity in every object and process, from acquiring the target material through every procedural step till completion of counting, ultra-low-level purity is of paramount importance. Anti-coincidence filters in counting are crucial for the last step, but they would be useless if the sample would be contaminated to begin with. The best way to reduce background, this was always my motto, the best way to reduce background is to avoid it. This is the idea behind the miniaturization of our proportional counters. Less material, less background. This shows some of the Gallex components, arrival of the big gallium tank. We had 2 of them, 1 for spare. This is the Gallex logo. Then we have, to the right, we have the big building is in front, is where the tanks are. And barely visible in the back is another building. This is the counting building where we had our counting arrangement. In the middle is just a picture of this miniaturized germanium-71 suprasil quartz proportional counter, and below is the counting tank, a Faraday cage surrounded by shielding material, and it had 24 positions in this counter, in this setup. So we could, if one run produces 1 counter field to be measured, we had 1 position occupied. That doesn't mean that we couldn't bring the next one and have the old one out. But we have 24 holes for 24 counters. So while the old runs count for a year or so, 12 months, the new one had always a place in this setup after 1 month of new run. So just show a few more slides. The tanks were installed in September 1989. The germanium extraction system with Edmund Henrich in the back, a big technical arrangement. And then during the first year of full-scale operation, 14 runs to measure the production rate of germanium-71 were carried out, and the Gallex 1 result was submitted by the Gallex collaboration to Physics Letters on the 31st of May 1992, back to back with the interpretative collaboration paper. Simultaneously on the 8th of June 1992, this historical first observation of PP neutrinos was announced at the Neutrino 92 conference in the Alhambra Gardens of Granada. The result implied a definite contribution from PP neutrinos and thus their discovery. This converted what nobody doubted to know, how the sun produces its energy, into an experimental fact. That's not the same. Now, this is this announcement with the Gallex logo at Neutrino 92, 83 plus minus 19 error and plus minus 7 systematic. That was the first slew. The summarizer of the conference, Anthony Morales, showed this slide at the end, the summary of the 1992 conference. Then you see, you can read. So in the foreword of the conference proceedings, Anthony Morales judged that, quote, the first Gallex result will mark a cornerstone in neutrino history. The participation in it of various historic sciences of neutrino physics will prevail in our memory. They included Bruno Contecorbo, David Schramm, and Fred Reines. The result was that total result was about what one the standard, the luminosity of the sun predicted for the whole signal. So about just the PP rate expected alone. But this is only 60% of the total because are noch the beryllium-7 neutrinos. So 60% of the total standard solar model expectation showed there is a definite deficit of PP and or beryllium-7 neutrinos. With Gallex 1 data in hand 1992, this slide displays the respective implications. The observed production rate is about what the standard solar model predicts for PP neutrinos alone, but it is about 40% short of what one expects from the solar energy output, the solar constant. This reduction is highly suggestive of neutrino mass-mediated oscillations between electron, muon, and tau neutrinos on the way from the solar core to the detector on Earth. This is because the detection reaction, namely inverse beta decay on gallium-71, detects only electron neutrinos and is blind for the other neutrino flavors. However, at this time, within the 2 sigma confidence level at the Gallex result was barely, but just compatible with the full standard solar model. In the sense, neutrinos that have come through unaltered were still allowed. Ironically, the positive observation of PP neutrinos, a cornerstone of modern astronomy, became overshadowed by non-objective, wishful thinking of some, prematurely interpret the deficit relative to the standard solar model expectation, 83 versus 127, as matter-of-fact indication of neutrino mass. A neutrino shortage from either PP or beryllium-7 neutrinos was evidently indicated, but the significance was 2 sigma only. In its interpretative paper, the Gallex collaboration discussed the issue in depth and refrained from a respective claim in the professional spirit that claims of seminal importance must be at least 3 sigma confidence level. Of course, it is nevertheless legitimate and state of art to discuss quantitatively the consequences if the central value would persist while errors will shrink. Condition to this, the respective exercise is obviously contained in the Gallex interpretational paper. It concluded that in a MSW-controlled neutrino flavor mixing scenario, neutrino masses of a few milli-electron volt over c square would apply. Alexei Smirnov will cover this issue in detail later today. Now, after Gallex 1, we worked hard to replace unsupported premature claims of authors by improving statistics through adding more and more runs and systematics, by experimentally demonstrating the reliability of the radiochemical method by means of controlled calibrations with strong low-energy neutrino sources using chromium-51, and chemical extraction yield control by spiking experiments with arsenic-71. The significance for the neutrino mass-mediated electron-neutrino disappearance from the Gallex 2, 3, and 4 solar run periods developed with improving statistics and allowed us to claim non-zero, now we claimed non-zero neutrino mass based on documented facts in 1995-96. And this is at the end of Gallex 4. This is the left part of this. This shows the results of the individual runs. You see, each individual run has a large statistical error. But as long as you measure, this is from 1992 to 2003, including G and O, your result gets better and better. And at the end of Gallex 4 data taking, the result was, now the error is the difference, 78 plus minus 8 SNU. This is more than 6 sigma, not 2 and not 3. 6 sigma below the standard solar model prediction. Hence, in 1997, disappearance of bulk sub-MeV neutrinos was finally assured at more than 99% confidence level. Now, this shows quickly, I think my time is, I have to apologize.
5 minutes.
Okay. This shows you see, in the middle of this tank, now the sun is out, the neutrino, the solar neutron come from the outside. Now we put a source in the middle of the tank. Now the neutrinos from the decay of this chromium-51 is similar, 750 keV neutrinos, like PP neutrinos almost, come in high flux directly in the tank. And the Megacurie chromium-51 neutrino source was a large-scale, unique experiment of its own, using totally new technology. It involved the production of 40 kilograms of isotopically enriched chromium-50 from 4.3 natural percent abundances to 40%. And record neutron doses for activation of chromium-50 to chromium-51 under rigorously enforced purity conditions. CNRS took responsibility to neutron activate this enriched chromium at the Silo reactor in Grenoble and to produce a Megacurie chromium-51 neutrino calibration source, the strongest artificial neutrino source ever. 2 chromium-51 neutrino source experiments were performed in 1994 and 1995 and verified the proper operation of Gallex, also in systematical error. Overall, it is demonstrated there are no surprising bugs in the galactic up. The data are trustworthy. Very short, the arsenic test. I think I skipped that. We put arsenic 71 because of time inside the tank, but this could be done only after the end of solar runs because it contaminates the target. Usually we deal with 10 atoms, and now we put in 30,000 atoms. So that is a mess for the background in the following time. So this was limited, but in any case, I have no time, but this was a yield control experiment, very simple. Every chemist would do that. If you can do it in the rates, okay. And the result is the recovery, chemical recovery process. Always worry about backholding effects chemical. And this showed recovery is more than 99%. Perfect recovery. This further established the long disputed reliability and reproducibility of the radiochemical method for neutrino detection in general and of Gallex in particular. It was this final assurance of the reliability and significance of the PP neutrino flux deficit that provided the first undisputed experimental evidence for the new physics Alex Smirnov will talk about later. Now, in 1998, the Gallex collaboration changed to a new organizational structure in order to adapt to a more routine-like gallium neutrino observatory, GNO. This was mainly an administrative adjustment whereby the essential experimental conditions remained basically unchanged. GNO data taking lasted from 1998 till 2003. Altogether, Gallex and GNO have collected in 10 active years solar neutrino data in 123 runs. The next slide shows again the sum, all the single run results. Now, to the end, we conclude that the satisfying notion that the early Granada Gallex 1 result of 83 plus minus 21 SNU is fully consistent with the 12 years complete results of 68 plus minus 5 SNU, 0.7 sigma above the now much more precise value. Now, I want to talk about whom we own thanks. There was INFN who made Gallex possible. INFN with Nicola Cabibo, Luciana Maiani, for making LNGS a still unique facility worldwide. The first director was Enrico Bellotti. MPG, BMFT, this is the German research funding, Krupp Foundation, INFN, CNRS, and the enthusiastic support of the pioneers that got the LNGS laboratory going, Nicola Cabibo, Luciana Maiani, and Enrico Bellotti. For all of us, Gallex was a wonderful scientific and human experience. It was an international collaboration in the true sense of the word, a great social experience for all of us, across all borders. In a nutshell, Gallex demonstrated how the world could constructively operate when a good-willed, educated people bring in their diverse individual talents and experiences towards a truly worthwhile goal, respecting and learning from each other. In my experience, the prospects of success of any collaboration are decided in the embryonic state of its formation. Condition is that the people that come together are primarily driven by the common scientific goal with egoism being human but put to lower priority. Credit must be given to all who deserve it, to all who deserve it. For good spirit in the collaboration, it is as simple as that, but this wisdom is rarely applied. Usually the heroes take it all. Now, I just want to memorize those which are no longer with us. Over the years, Gallex became a family. Many friendships and even some marriages across nationalities came out of it. Sadly, in families, there is also drama. Here I memorize those Gallex members who are no longer with us in deep respect and acknowledgement for their achievements within the project and as friends. And the final slide shows my 40 years, my wife, Emiko. She was the soul of the Gallex family. The Gallex members liked her more than me, and she died in December 2016. I take the liberty to note this here in the name of Gallex members. Thank you.
Thank you very much, Till, for this beautiful account of the journey. And we are almost on time, so I think I can allow one or two questions if there are any, or comments from the many protagonists of the events. Daniel.
Thank you, Till, for this very nice contribution to the history of Gallex and the history of science. Just a short comment. It was not CNRS, but CEA, which was participating to the experiment.
Eugenio.
Thank you, Till, for this wonderful talk. I just want to remind the figure of Werner Berezinski, which was which was one of the first to determine that no variation of solar model could justify the data of the solar neutrinos experiments, and so that was really the first evidence on beyond standard model physics.
This is of course true, but it's not that I forgot him because we had close collaboration. He was not officially a member of the Gallex collaboration.
Very last comment, if any. If not, we have the coffee break, and then Luciano will give his talk as soon as he comes back. È tornato Maiani? I would ask Giampaolo Bellini to be ready to go first in case Luciano delays. Coffee break. So thank you very much. We resume the session with the talk of Luciano Maiani. Thank you very much, Luciano, please.
Thank you very much. Can we have the slides? Okay. So this is a talk about Gran Sasso as a laboratory, the beginning. And I was, in these years, I had the pleasure to work with many people in Gran Sasso and in Rome. And I would like to mention here Nicola Cabibbo, Puccio Bellotti, and Ettore Fiorini, with whom I had a lot of discussion and help, etc. So I would like to dedicate to them this talk. Can I go? Come si fa per andare avanti? Next slide. Okay. So, thank you. So, we started, the story starts in 1974, where the theory of grand unification was proposed by Sheldon Glashow and Howard Georgi. And it was a great interest. And the most striking prediction of this theory was that proton could decay. Of course, it had to have a very long lifetime to be compatible with the limits of the stability of matter known at the time. And indeed, the theory predicted a long lifetime because this interaction was mediated by very heavy new hypothetical vector bosons, which were at a very high mass. So the observation of this phenomenon required to monitor large quantities of matter, big junk, and in an environment well protected by cosmic rays. And so the race for big underground laboratories started in Japan and in the US. In Italy, on a much smaller scale, Carlo Castagnoli had already used a room inside the Mont Blanc tunnel, which was called Garage 27, was a rather small, but it was very, very well protected from cosmic rays by the Mont Blanc, and it was inside the tunnel. And Ettore Fiorini and his group installed in Garage 27 one of the first proton decay experiments, NUSEX, that in the late 1970s produced significant results. In parallel with the beginning of the large underground installations, Kamioka and in Japan, and IMB in the US. In 1979, Nino Zichichi, that was at the time INFN president, submitted to the Senate of the Italian Republic a project for the realization of a large underground laboratory that had to be accessed from the tunnel of the highway L'Aquila-Teramo that was then in construction. It was a very ambitious project that Nino succeeded in making it approved by the Italian Parliament. The financial laws in 82, 83, works went on until 1985, and the laboratory became effective in 1987, with the first experiment, macro, to detect cosmic monopoles. And I see Enzo Iarocci in the audience that will remember his participation to macro. However, from the outset, it was clear that Gran Sasso Laboratory was not ideal for proton decay. It was too small and not extendable like the Garage 27, because once that the highway went into operation, you could not stop it for years to make a larger laboratory. However, fortunately, there were interesting lines of research that emerged. One I mentioned, the search for cosmic magnetic monopoles, and then solar and perhaps long baseline neutrinos. Indeed, the halls of Gran Sasso Laboratory are all oriented towards CERN, so as to be ready to receive a beam from CERN. Then there was the double beta decay, and then the search of dark matter. I will not speak about solar neutrinos. You had already Kirsten talk, and Bellini will also speak about that. I will speak about double beta decay, long baseline neutrinos, double beta decay, and a very little bit for search for dark matter. This is a slide which illustrates what happened at the birth of Gran Sasso, and there is here a very nice drawing personally made by Nino Zichichi that shows the idea that there was already the idea of having a neutrino beam from CERN to Gran Sasso. And here you see Nino receiving the Bruno Pontecorvo Prize in 2007 for his contributions to neutrino physics from Pontecorvo. The long baseline neutrino beam, in fact, I will come back on that, came much later, and it was approved in 2000, end of 1999, and was built between 2000 and 2006. Here you see me with a sous-prefect of Gex and Alessandro Bettini, who was at the time the director of Gran Sasso. And I will give you back this is the outline of the CERN beam with the famous decay tunnel in which neutrinos are produced. And of course, in CERN, the neutrino beam had to be oriented underground because, of course, of the curvature of the Earth required so. I want to say a few words about Nicola Cabibbo and Gran Sasso. Nicola Cabibbo became president of INFN in 1985, so at the very beginning of the laboratory. Of course, everybody knows that Nicola Cabibbo was not only the president of INFN, but also an eminent scientist, regular speaker at the LHS school, and he continued Nino's support to Gran Sasso and promoted new initiatives in the field of solar neutrino physics. In particular, it is due to the impulse of Nicola, the approval and execution of Gallex, and the start of the R&D phase of the ambitious project Borexino. Under Nicola's presidency, Gran Sasso became a first-class international laboratory, open to collaborations from Europe, USA, and Russia, as it is right now. But I want to conclude this introduction with a spectacular initiative of the Roman lads, started in 1990 and realized with Nicola and Ettore Fiorini as the main protagonists. These are a few pictures. Isola di Maldiventre, which is a misspelling of a real name in Sardinian dialect. It's a very beautiful island on the western part of Sardinia, and just by chance, a sub amateur sub, discovered a large Roman ship under the sea with a big charge of lead ingots. And you see here, in fact, the sea is very shallow, so it's not difficult to recuperate the thing. Sorry, there must be. So, this was the picture, and Fiorini understood immediately the importance to obtain in custody in the Gran Sasso the lead ingots. Why? The modern lead has a significant contamination of lead 2010, which is formed in the ore from the decay of uranium-radium decay chain. It's polluted by this lead, and this lead 2010 has a lifetime of 22 years. So this lead, the Roman lead, had been for 2,000 years on the floor of the sea, and so it was essentially free of this contamination. For this reason, Ettore Fiorini asked Nicola to promote an agreement with Regione Sardegna and with Moore to contribute with the IN funds the recuperation of the vessel and its charge, and to assign the ingots to LNGS to use them as a screen to low background detectors. Nicola backed up the initiative, and here is a statement by Ferroni when the last stock of lead ingots was given to Gran Sasso, that was in 2016, and praised the initiative as an exemplary case of collaboration between institutions, finalized to valorize the national archaeological heritage, and at the same time to contribute to frontier research in the fundamental field of neutrino physics. Now we go to neutrino oscillations, and you cannot speak about neutrino oscillation without remembering Bruno Pontecorvo, that you see here in a few pictures. Neutrino oscillations have been introduced by Bruno in 1967 as a possible explanation of the deficit of solar neutrino flux that was emerging in 1969 from the Collar Goldfield Mines experiment, Davis and John Bacall, and Davis for that had the Nobel Prize later. What the Pontecorvo suggestion, what was we call now the just so solution. That was his proposal, that Earth it just happens to be at the minimum of the oscillation, and that explains why we see only, say, 30%, I don't remember the exact number, of the neutrinos that are supposed to be produced at the sun. That was not a very natural solution. A more natural solution was found later by the MSW. Well, sorry, this is not correct. It's MSW. The oscillation may occur in the solar atmosphere, and at the outcome of the solar atmosphere, you have the one eigenstates of the neutrinos, which has a certain angle, mixing angle between nu A and nu mu, or alternative, another possibility, and that happens for boron neutrinos. And alternatively, the neutrino deficit is just an average over the Earth position. So you average the oscillation. And these are called vacuum oscillation, and that's what happens for proton-proton neutrinos. Nicola, in 1976, studied first a neutrino oscillation with 3 flavors and showed that, like it happens for the CKM matrix, the neutrino matrix could have a CP and CPT violation, which, however, we have not yet detected. There are hints, but not full measurement. And I give you here a table which represents fits from Fogli et al. And from Schwetz et al. And the statement of that was done in the conference where we recalled Bruno Pontecorvo is that now neutrino oscillations are fully consistent with the oscillations of 3 neutrinos mixed with real angles. The just so solution is excluded, and there are hints but not measurements of a possible phase of CP violation. These are the thing. They come from a long collaboration between many experiments. So this is the angle that results from solar neutrinos. That is the angle for atmospheric neutrinos, which I will discuss in a moment. And then there is a last angle, the third angle, which has been measured more recently, also determined. And I would simply recall that you need to have all 3 angles different from 0 to have CP violation. So the measurement of this theta 1,3 showed that, in fact, it is possible to measure CP violation. And that was the last result that I want to quote. This is a nice picture of Nicola as president of INFN when he was working on with the Gallex collaboration. And I wanted to give you also a picture of Puccio Bellotti, and Fiorini was in the previous picture together with Pontecorvo. Now, it is very interesting to know what are the lengths of this neutrino mixing, and it's very interesting that they are all terrestrial lengths. If you use this formula, the simple two-body mixing, you see that what is important is the phase of this sine square, which depends from the distance and from the energy of the neutrino. So you can compute for each neutrino solar or atmospheric, which have typical energies listed here, what is the length at which this phi becomes pi over 2. And it's 90 kilometers for solar neutrinos. In fact, the most precise determination of solar neutrino of the 1-2 mixing has been obtained by Kamland, observing neutrinos nu E, anti-nu E, emitted by nuclear reactors around Kamioka. And then the atmospheric neutrinos give a length of 500 kilometers, which is typically a length of a large travel inside the Earth. I got interested in neutrino oscillation in 1980 in one of the periodically occurring beam dump experiments, which are indeed very interesting experiments. In the beam dump of 1980, the protons from the third SPS were used and put into a dump, copper dump. Now, what happened there is that most of the particles, long-lived particles that are produced are pions and kaons, and they are absorbed by the nuclei, the surrounding nuclei, so you don't see them. However, and that is the purpose of the beam dump, if there are heavy particles, like charmed particles, some 10⁻² lifetime, they have time to decay, and produce nu mu and nu e. And if they have a large mass like charm, they have both muonic and electronic decay with essentially equal rate. And so the beam dump produces a beam of neutrinos, nu mu and nu e, in equal mixture. So observing the interactions of them with external detectors, you can compute the relative number that comes out of nu mu and nu e and see if there is some change in the ratio 1-to-1 of nu mu and nu e interactions produced by the oscillations. At the worst aspect of the beam dump that, of course, at the time we did not know, is that the lengths are not very large. And if you compare with the oscillation lengths that I gave you in the previous slide, you can see that the beam dump had no chance to observe neutrino oscillation. And in fact, the conclusion of this paper were not so conclusive. In fact, there is no oscillation in the beam dump. At the time, I remember how unorthodox was the concept at CERN. We spoke about neutrino oscillations, and everybody believed that in any case, neutrinos are massless and we are not going to oscillate. Later, I was visiting ITEP in Moscow, and there was the first hints of a suppression of atmospheric nu mu versus nu e in Kamioka, but I must say I was not very much impressed. It's only later that in 1993, when in a conversation with Bellotti, the argument came out and he told me, look, these data have to be taken seriously. And I got interested again in neutrinos oscillations. One slide about that, it's very interesting. When cosmic rays go into the upper atmosphere, they produce pions, which have the time to decay because the atmosphere is very thin, and they produce one muon in the first decay, then the muon produces another nu mu and a nu e in a secondary decay. And so, similarly to what happens in the beam dump, you produce a beam which has a very definite mixture of nu e and nu mu, and which have substantially the same energy spectrum. And then you should see 2 times nu mu interactions interacting with your detectors as you see nu e. And this is what Kamioka found for downward going neutrino, from the neutrino that come from your head. However, in Kamioka, you could also see neutrinos which come from the other side of the Earth, and in fact, the zenith angle gives you directly a measure of the distance that the neutrino has traveled from the atmosphere where it was produced to your detector. And in 1994, as Bellotti was saying to me, they got very convincing evidence that there was a mismatch between the abundance and spectrum of nu mu's and nu e's. And that was the first solid hint of a nu mu oscillation, disappearance of nu mu, because you see that nu e are perfectly normal, and so it's nu mu which disappear. And of course you can ask, where do they go? And we knew at the time already that there is a third lepton, and so the most reasonable thing was to say that they oscillate into nu mu, and Kamioka produced a measurement of this oscillation. And I took these things from the Nobel lecture of Kajita. In fact, Kamioka data had to be taken very seriously. As I said, However, as I said, the most reasonable thing was to say that nu mu oscillate into nu tau. However, the atmospheric neutrino spectrum does not go high enough to see real tau produced when these nu tau interact with matter. And therefore, the idea came at the end of 1998 to propose a long baseline neutrino beam from CERN SPS to Gran Sasso, as Nino had anticipated many years before. And you see the spectrum that was obtained for the CERN neutrino to Gran Sasso beam. It has a peak around 20 GeV, and so it's perfectly apt to produce nu mu, nu tau oscillation with the nu tau then interacting and producing a real tau. In summer 1999, I had discussion with Paolo Strolin and with NIVA. In fact, I went myself to Nagoya to spoke with him, and I was convinced that one could make an international collaboration promoted by Napoli and Nagoya to realize an emulsion detector, which is what is needed due to the very short lifetime of the tau particle, and that could justify the beam, the construction of the beam from Gran Sasso from CERN to Gran Sasso. And the project was approved in December 1999, the construction with a very substantial contribution of Italy via INFN. This, as I said before, is a picture of the layout. The protons come out of the PS and make kaons and pions that are allowed to decay in a tunnel with vacuum, appropriate vacuum. Then there is a stop, and neutrinos continue towards Gran Sasso. As I said, from the SPS, they are aimed directly at Gran Sasso. Yes. I want to explicitly name a few persons that have been really at the basis of this project. First of all, Jarocci, that was then president of INFN, and Sandro Bettini, who was the director of Gran Sasso. Of course, for the experiment, Strolin and Niwa, and then De Clé and Ereditato and De Lellis were the opera spokesperson. I hope I did not miss anybody. And at CERN, I got very strong support from Kurt Hubner, Carlo Wyss, director of Accelerator, and Claude Detraz, director for fixed target programs. Elsener was at the end the head of the construction of the neutrino beam, and Robert Aymar was at the time chair of the review committee that examined CERN from a completely different point of view, and was CERN DG and was in great support of this project. Opera ran from 2008 to 2012, and almost observing the CNGS, an almost pure nu mu beam at the start, and the mixture after 700 kilometers, 730, and collecting a total of 10 to the 20 protons on target. And all in all, they have observed 10 beautiful nu tau charged current interaction producing a tau. This is the first that they observe, and perhaps is the most beautiful one. You see that is the interaction of the neutrino. Then there is a small time for the lifetime of the tau, and from this point, the external vertex, you have one line which is a pi plus, essentially, a daughter of the decay, and then you see two beautiful photons which indicate the decay of a pi zero. So this is a tau that goes into rho plus nu tau, and subsequently rho decays into pi zero, pi, and pi zero goes into gamma gamma. It's a really beautiful experiment, beautiful event. This is another event which has, this is the primary interaction, decay path, and then you have three hadrons coming out. So it's tau that goes into three charged hadrons, plus, of course, a nu tau that you don't see. And then a third candidate is just tau that goes into nu tau and mu minus, and you see the trace of the mu minus, and this is the primary interaction. So enough for long baseline. I think that we now know that the oscillation is indeed in tau neutrino, and this combined with the fact that that zero decays indicate that there are three low mass neutrinos that seems to close the generation to three generations and nothing else. Now let me go to the last argument, double beta decay. This is the process where we can decide whether the neutrino is a Majorana or a Dirac-Weil particle. And for long it has been a subject of super specialized people, among them Ettore Fiorini, who was the one among those that opened the field, and today is a thriving lines of particle physics with several experiments in Gran Sasso and other in underground laboratories around the world. But let me tell you what is double beta decay. That's a very small theoretical introduction. I learned these things very recently. This thing is known as the mass parabola. That is, it displays the mass of nuclei which have a fixed weight, total number of nucleons, in this case 102, and a given Z, number of protons. So the number of protons is low here and high here, higher than the magic number, which is essentially equal number of neutrons and protons. And there are two parabolas according to whether Z has the same parity of A or the odd parity. So this is for even parity, and this is for odd parity. And you see here that the nuclides here, with respect to the next one, is a little heavier. And that is because this has too many neutrons. Neutron is heavier than the proton. And so this can decay into, beta decay into the next thing. If you go on the other side of the parabola, you find the opposite situation, that the nucleus with Z is much lighter than the nucleus with Z plus 1. And this is because when you increase the number of protons, the electrostatic repulsion increases and the energy increases. And in this case, you have a beta plus decay from this to that. However, when you are at the bottom of the parabola, you can have cases in which the from Z to Z plus 1, the mass increases. And so germanium-76 cannot decay, beta decay into arsenico-76, and in this case, it can decay by jumping of 2 units of Z into selenium. And this is double beta decay. Double beta decay is a second-order Fermi interaction. Here it is. And it can happen in 2 versions. For Dirac neutrinos, this is the only possibility. And you produce 2 electrons and 2 antineutrinos. However, if the neutrino is Majorana, you can have a direct exchange, virtual exchange of neutrinos from one vertex to the other, and you have double beta decay without emission of neutrino. And that is the signature of the Majorana neutrino. I have also a small parenthesis in theory. This is the current with Majorana neutrino, but of course neutrino Majorana is the same as antineutrino, and so this current is the same as this. And if you make the product of the two, this is the double beta decay with a virtual Majorana here. However, you have a 1 minus gamma 5 here, and a 1 minus gamma here, and the gamma 0 here. And so the term proportional to k slash is killed by the projector, and you see that of the propagator of the Majorana neutrino remains only the mass term. So the double beta decay without neutrinos measures the Majorana mass of the neutrino itself. This is a list of nuclides with exhibit double beta decay, and you can see here the number of experiments that are trying to get Majorana neutrinos. This is a very interesting curve. I think it was produced by Fiorini at first, that shows that in germanium, which you use as a detector of the electrons, in fact, the germanium can be at the same time the source, because it does as a double beta decay, and you would see double beta decay as a line in the energy of the 2 electrons. It's very, very interesting signal. Gerda is one of the experiments. It's finished now. The other one is Cuore, and I am reporting the present numbers that we have, but I give you just the figure. This is a figure that is used to analyze these numbers. You can plot the the mass of the beta-beta particle as a function of the mass of the lightest neutrino, which you determine separately. And there are 2 branches according to what is called the normal hierarchy. The neutrino of the 3rd lepton is heavier than neutrino of the 2nd, or inverted hierarchy. And at the moment, we are essentially here as lower bound. So the mass of the beta-beta neutrino has not been determined. For Gerda, it is between 70 and 160 milli electron volts, and for Cuore, it's about between 75 and 350. And of course, it would be very interesting to get into this region which is the object of other experiments like Juno, to determine the hierarchy. Cosmic rays can also give a determination of the total sum of neutrinos, and according to inverted energy or inverted hierarchy or normal hierarchy, they are a little bit below. they are in this region, but of course with other kind of uncertainties. I'm closing with one slide about dark matter. I cannot go into the details. I showed you limits the cross-section as a function of the WIMP mass for xenon 1 ton and for the Chinese experiment Panda X. A couple of years ago, there was also another suggestion for the dark matter that could be that black holes could be created from the gravitational collapse of the Higgs field, so no dark matter at all, but just black holes of normal matter, and was proposed to that, and there are important limits, but we don't really know. So I think I can close here. I would like to thank you for your attention, and that's it. Thank you very much.
Thank you very much, Luciano. We are almost on time, so maybe a couple of questions can be taken or comments. È la festa di Giampaolo e Till. Vai. Ecco, grazie.
Okay.
Next.
We can go to...
If not, thank you very
Borexino.
much. Thank you very much, Luciano.
Thank you very much.
And Giampaolo.
Ok. Okay, the challenge of Borexino experiment. Why challenge? Because, cominciamo male. Scusate, ma non va questo. È questo qua. No, ho capito, ma questo qua è l'indicatore. Questo è l'indicatore. Okay, why I entitle the challenge? Because the goal of Borexino was a very ambitious goal. The idea is to measure the spectral, to have a spectral measurement of solar neutrino, including very low energy, and to have a threshold well below 1 MeV. At the time, we started the discussion between 80s and 90s. There were other experiments in preparation, Cherenkov experiment and radiochemical gallium-based experiment. But no one of these experiments would be able to reach the same goal of Borexino. Now, first of all, we understood immediately that was necessary an extreme radio purity, never achieved before by other experiment. And in fact, at that time, already happened that two French groups decided to face such a feat, but quickly given up. And we also were surrounded by a large skepticism of the large part of the scientific community. Sorry. And this skepticism really go ahead, continue during, also during the period, scusate ma questo qui funziona, ecco, funziona molto male. Go ahead during, also during the experiment, as we proceeded with progressively more difficult experiment. But I would like to say that in any case, our luck was to find two persons. One was Enrico Bellotti, who at that time was director of the Gran Sasso Laboratory, who gave us the needed underground space. And the other one was Luciano Maiani, at that time president of INFN, who understood the potential of the project, shared the risk with us, and decided to start to finance the experiment. Which are the strategy of Borexino, the strategic choices? Now, first of all, is to have to use a very compact radio purity. Excuse me. First of all, to use a detector with a very compact volume in order to use as much as possible material, because all material are radioactive. Second, to use a scintillator in order to have a high light yield, in particular in organic liquid scintillator, because it was easier to be radio purified. And in particular, we chosen a solvent, a hydrocarbon as solvent, and a fluorescent dye for solute. And what to reach is 500 photoelectron per EV with 30% of coverage. Then was needed a very strong radio purification, because it was necessary to gain between 6 and 10 orders of magnitude in order to reach the needed radio purity, respect the normal radio purity of the materials. And finally, in order to understand if we are able to obtain this radio purity, was necessary to build an instrument able to measure this radio purity, and what we call counting test facility. Now a bit of history. We started the discussions, as I said, in 88, between 88 and 90. In 1990, we started to an R&D program in order to implement methods able to achieve a radio purity at an order of magnitude higher than the most present, than normally present in solid and liquid. And at the end of this period, with this counting test facility, we were able to demonstrate that where we have achievement the radio purity as per design. Then we started data taking in, sorry, excuse me. Okay. Then we started the data taking in 96. In 96 we started to build the detector, and it was needed 11 years. Because, first of all, because in Borexino nothing is standard, and everything has been developed ad hoc. Second, because we have been stopped for 2 years and a half by the thermal court for environment problems. Then in 2007, finally, we started data taking, and we had two phases. The first phase, sorry, but questo non funziona. Scusate, ma non funziona. The first phase, the third phase was between 7 and 10, and the second phase between 11 and 16. Between the two phases, we proceeded with 17 months of a second scintillator purification, and we used the data obtained in these two phases in order to measure the single fluxes of the PP chain reaction emitting neutrinos. Then in 2016, we started the third phase with a thermal isolations of the detector, and with this data, we detected the CNR cycle. This is a layout of the experiment. I go quickly because I think this is already more or less already known. In the center, there is 270 tons of liquid scintillator, included in a nylon, what we call an inner vessel, we obtained by ultra-pure nylon, with a thickness of 125 microseconds. This in order to have a very small amount of material in contact with scintillator. Then around the inner vessel, we install another vessel, the outer vessel, as barrier against the emission from photomultipliers and the stainless sphere. The stainless sphere was just a sphere containing the two vessels, which support also 20,212 photomultipliers. Between the inner vessel and the sphere, there was 600 tons of buffer liquid in order to shield just the emission of the photomultipliers and for the steel of the sphere. Finally, everything has been included in a water tank, large water tank, with contain 2,400 tons of ultra-pure water, and within this water, we installed 200 photomultipliers in order to have a warm vito. All this has been conceived. Sorry. Devo spegnere. Me lo spegne per favore. Then all the detector has been conceived as an onion with a greater shielding. The closer the layer is to the center, the greater is radio purity. Okay, it's very, very simple. The detector principle is very simple. For neutrino is the elastic scattering with electron, and the expected count is 50 count per day per 100 tons. For antineutrinos is a very tagged reactions, which is inverse beta decay. The fiducial volume changed. Excuse me. The fiducial volume changed from the total EV to 78 ton, depending on the analysis, and the threshold finally was down to 150 kV. The most dangerous contaminants in the scintillator were uranium and thorium and their progeny. And for them, it was necessary to reach 10 to minus 16 gram of contaminants with respect to a gram of pure liquid. And in addition, also for potassium 40, because for it was necessary 10 to minus 18 gram over gram. For radon, also was necessary to reach less than 1 count per day per 100 tons. But in addition, also the dust particulate containing potassium, thorium, and uranium oxides. And in addition, there was also the noble gas as argon and krypton. But there is a special attention to be paid to carbon 14, because the carbon 14 cannot be purified. Then, which are the tools in order to questo non funziona perché è troppo sensibile. In order to fight again this contamination. Scusi, me ne dà un altro per favore, questo non funziona, scusi. No, non posso andare avanti così. Questo non funziona, quello non funziona, non so. Devo andare indietro. No, lei sta andando avanti, devo andare assolutamente indietro. Ma questo appena lo tocco, mi avanti 2 o 3, non è possibile continuare così, scusi. I'm sorry for the other people. Okay, the tools were the ultrafiltration at the level of 0.05 micron, the distillation at a level of a temperature of 80 degrees, no more, in order to not extract the contaminants which are embedded in the distillation column material, and then which are dangerous, of course. Water extraction to remove water-soluble contaminants. This is used in counting current column. Finally, the gas stripping, also in a counting current, done with a very ultra-clean cleaner, and then an advanced cleaning in order to have a final cleaning of dusty particulates. In addition, okay, at the end of this period, we fill the detector in batch with already, for the scintillator already treated with ultrafiltration, distillation, and stripping. And a second purification is done, as already said, between the first and second phase, in that case with ultrafiltration, water extraction, and stripping. Okay, now the carbon-14. As I say, the carbon-14 is a particular problem because cannot be purified. The carbon-14, as you know, has a very long lifetime, and it produced inside the oil by the cosmic rays, neutron, and in general rock. The equilibrium level with cosmic radiation is about 10 to minus 12 ratio carbon-14 on carbon-12, but what we needed is 10 to minus 18. Then the only way is to use very deep layers, and we did a big effort to convince the production company to use they layer very deep, in particular what they use are the Libya layers. In addition, in the site of the company, we installed dedicated pipeline and loading station in order to avoid a further contamination. Both the pipeline and all the line of the loading station has been treated as all the detector component with special care. And for the loading station, we filled the ISO tank, which also has been treated in the same way, and we organized the transport in such a way that in 22 hours was able to bring the scintillator produced in Sardinia to underground laboratory in order to avoid production, cosmogenic production of nuclide as the barium-7 radioactive. Okay, now, at the moment, we build the counter-test facility. Why we needed this instrument? Because at the time, the most sensitive instrument in order to measure the radio purity was a mass spectrometer with plasma source, but this is able to reach only 10 to minus 10 gamma over gamma, and we needed more. Then the counter-test facility is a detector simplified and smaller than Borexino, with only 5 tons of liquid scintillator, 100 photomultipliers, and 1,000 tons of high purified water. The liquid the purified liquid scintillator has been tested in a counter-test facility at result to be at limit of the counter-test facility sensitivity, which was polymeric thorium 5, 10 to minus 16 gamma over gamma, and for the ratio carbon-14 or carbon-12, 2 times 10 to the minus 18. This means that in that case, the need radio purity was reached, and then the Borexino was durable. Okay. Now, once reached the radio purity for the scintillator, was necessary to build a detector able to maintain the radio purity record achieved for the scintillator. And for this, we have to use appropriate techniques and methods. And in practice, what happens is that all components have been custom designed, prototyped, built, tested following, in most cases, unconventional approaches, treated and assembled with method developed in-house. I have no time to describe the situation, but I give only a few examples. One is a nylon for the inner vessel and the outer vessel. The nylon, once chosen, has been extruded in controlled area. Non funziona questo qui. Questo non funziona. Ma no, devo usarlo come pointer, scusi. No, questo voglio usarlo come pointer. Ma si vede malissimo. No, io voglio usarlo come pointer.
Subito sopra. Eccolo qua.
Sì, qualche volta va, qualche volta non va. I'm sorry, but this is out of my responsibility. Okay, it's been extruded in control area, handled in class 100 clean room, equipped with the first ever built radon scabbling device, and with absorption filter, precision cleaning by a non-contact ultrasonic process. In addition, the inner vessel has been nested ab initio into the outer vessel in order to protect it, and the interface between the two vessels has been filled with ultra-pure hydrogen. I would like just to say that also the first filling of the inner vessel has been done with synthetic air, because synthetic air have not radon. Same problem for the photomultipliers. The photomultipliers has been developed with an external company, and in order to have, first of all, a low radioactivity glass, and using also a particular crucible. Second, to have low radioactivity ceramics and for the dynode cascade. Then also a low jitter time in order to better spatial resolution. And finally, okay, this PMT has been isolated with resin and water in order to resist OPC. But this is normal. Now, for the plants, situation was even more complicated, because each details had to be carefully studied, has to be analyzed, and also material component had to be selected in order to have a sensitive detector for low radioactivity. Also here I can do only some example. All surfaces of the line and of the vessel has been treated with pickling, passivation, electropolish, sometimes chelation and mirror shooting in order to have roughness less than 0.8 microsecond, and cleaning with a class less than 50. In addition, the tightness of the single joint were better than 10 to minus 8 millibar per liter a second, and in general was better than 10 to minus 6 millibar per second. Why is this? Because it was necessary to avoid the external air leaks, because external air were largely contaminated by radon at a level of more than 100 becquerel per meter cube, and also by oxygen, because the oxygen absorbs the scintillator light. Then also all the pumps and gasket, internal component, were replaced by Teflon or Viton. All flanges, valves, fitting pumps were equipped with a nitrogen purging port, Why? Because in case of failure, they don't have in contact with the external air. We use also extensively the nitrogen, and because the nitrogen was a purified agent to remove gases, also dynamic blanket for all vessels, and the detector, plant pressurization, filling the gap between the EV, etc. In addition to the commercial nitrogen, we use two types of nitrogen. One is high purity nitrogen. This has been purified with a special plant installed in the site via 2 kilogram of cooled selected high purity activated carbon traps directly in liquid scintillator. And we reach an exceptional purity of polyradon less than 1 microbecquerel per meter cube. Second was what we called LACN, which is a nitrogen with low argon and krypton level. This was taken by a specialized company. We had already problem for recontamination during storage, but what is very important is that is continuously tested with neutron activation, a special very rare mass spectrometer with very high sensitivity. We had also strict control, as I said, of the radon 22, which is everywhere. And I would like to focus our attention that all material has been measured with on or very close to surface in order to catch the emanation of radon. This radon emanation is being pumped or flushed out in a clean carrier gas, included in a miniaturized proportional counter with sensitivity of few atoms. In particular, I would like to say that what we check the nylon used for the AV AOV, what we obtain something is below the measurability. Okay, and you have also the advanced cleaning where you use a special column, and we can complete this part. Say that these are only some examples of effort being done in order to start Borexino. But I would like that you understand that his part, his activity was very important because it has been the key for the success of Borexino and what really allowed the measurements discovery were obtained. Without it, it was impossible to have an experiment as Borexino. Now, this is a table of the results for the radio purity. I have no time to go through all the table. I will only to focus our attention on carbon-14 with reached 2 10 to minus 18, carbon-14 and carbon-12. Uranium and thorium, for which we gone beyond what's needed, of the level 1 10 to minus something 10 to minus 17 for thorium, for uranium, and something to 10 times 10 to minus 18 for the thorium. And then we reach, for the second phase, with the second purification, we reach even 10 to minus 20 and 10 to minus 19 gamma over gamma. Finally, for the radon, what we succeeded to reach is less than 1 compared to per 100 ton, was exactly what was needed. This is a picture of the internal part of the stainless sphere once the phototube were installed. I would like you pay attention to the dress of this operator. Why? Because in addition to the 5 clean rooms that we constructed around Borexino, also all the volume of the stainless steel sphere were equipped in order to have a clean room of the class 10,000. Okay, this is another picture of that. Naturalmente questo fa. Questo mi fa perdere un sacco di tempo. And this is the gap between the scusate, ma non so cosa fare. For the gap between the stainless steel sphere and the water tank. This is covered by tieback in order to maintain the water emitted by the nitrogen events due to the moon crossing the detector. And finally, this is the left is the detector during the filling, and the right already filled. Okay, now we go to the result. I start with the PP chain, and at the left you see what has been measured. These four reactions. HP was not measured due to the very low statistic. And this, on the right, you have the energy distribution. This is a threshold of a chemical experiment. This in green are all the parts covered by Borexino. The only thing is that at the end, this threshold was a little lower. Now, these are the distribution in black of the data reached in the first two phases. This in black. And this is a result of the multivariate fit. We explain later which is a multivariate fit. And this in red are the signal PP, beryllium 7, PAP, and boron that we discuss later. But unfortunately, we see that in addition to the signal, we have also residue of the contaminants despite the very high radio purity. Is polonium-210, this in yellow, carbon-14, bismuth-210, krypton-85, and this in pink are also piled up due to the carbon-14 rate. Even if the carbon-14 rate was very reduced, nevertheless is important and it produces pile up on the other experiment. But I'd like to say that these are measured, are fit altogether only at the end, because at the beginning what we did is before measure separately the beryllium 7, then the CNR, the boron 8, then the PAP, and finally the PP. PP was more difficult because due to his interference with carbon 14. In addition, there is cosmogenic carbon 11. I will show in a moment. Now, which are the tools in order to fight against this residue? Once in extended use ab initio of the Monte Carlo to simulate the ratio scontaminant residue. Then an alphabetical discrimination exploiting the fact that the decay of the scintillator is faster for alpha and slower for beta, and the signal are only beta, only electron. For the carbon 14, the carbon 14 cannot be purified because it's continuously produced by the muon crossing the over burden of the Gran Sasso, and the rate is 1.2 muon per meter square per hour. And in order to fight, to fight against it. First of all, we use a threefold coincidence. We reduce the rate of the carbon-11 to 10%. And this confidence is done using the incident muon, the decay of carbon-11, and in particular the annihilation of the positron, and the neutron capture. Then we reduce to another 5% using the pulse-shape discrimination, and in that case also exploiting the fact the formation of autopositronium, which in the liquid scintillator has a lifetime of 3 nanoseconds, and also to the fact that the 2 gamma produced in the positron annihilation has a distributed topology. Okay, then for the Bornate, we did not use the energy distribution, but the radial distribution in order to separate it from the external background, and also because the shape of the energy distribution is distorted by the oscillation which depend on energy. We have also to say that it was impossible to go below 3.2 MeV because for the presence of a residue of thallium-208. For what concerns the multi-fit, the multivariate fit, this is a fit simply using 3 distributions simultaneously, the reconstructed energy with carbon-14, carbon-11, sorry, and also with the carbon-11 subtracted, and finally with the radiant position. These are the results obtained on the PP. In the first column, we see the rates obtained by Borexino. The second one is the fluxes. These are the 2 expectations for standard solar model with high low metallicity, and we see that the comparison shows that there is a good agreement, of course, within the certainty of the model. I would like just only to focus your attention to the fact that the difference between high and low metallicity in case of barium 7 is of the order of 9%. In case of borate, of the order of 17.6%, and for CNO, we will discuss later, about 28%. This measurement we did of the solar neutrino also allow us to determine the Earth orbit with solar neutrino, exploiting the annual modulation of the flux due to the eccentricity of the Earth orbit. We did it during 10 years. Second point, what is interesting is that now we have measured the PP chain, which produce the 99% of all the entire sun power. And if we compare it with, then we can measure the luminosity via neutrino and compare it with the luminosity via photon. And we can observe that they agree. This means that the standard solar model paradigm had assumed a very good situation for what concern the energy, because this means that there are no additional energy losses or production mechanisms besides those normally used in the model. Now, another important result is this one. The fact that we have succeeded to measure the four reaction in PP chain allow us to measure the electron neutrino survival probability in a large range from about 150 keV to something as 15 MeV. And for the first time, what do we measure? We are able to measure the survival probability in the vacuum regime, which result to be 0.55, which can be compared with the matter oscillation, which is 0.32. The constant PA has been rejected, of course, as a level of 98 confidence level. And I think that this is a good test for the MSW, even if in the transition region, the error of the data are still large. And in order to understand which is the contribution of Borexino to this electron-neutrino survival probability, we can compare it with the situation before Borexino. This is the same plot, but before Borexino. Another interesting thing is that we measure the day-night effect in the beryllium energy region. And we found that this was completely null. This means that this region for delta m square is rejected as a level of the 0.5 sigma. And the consequence of this is that we are able to single out the LMR solution without the Campbell antineutrinos and then without the CPT assumption. Okay, now we switch on CNO cycle. The CNO cycle has been hypothesized already in 1938 by Bethe von Weizsäcker. It is, the reaction is the same as in PP chain. It consists of hydrogen burning, but in that case catalyzed by carbon, oxygen, and nitrogen, and with a temperature which is 1 order of magnitude more than that obtained in the PP chain. Subsequently, the astrophysical theories identify the CNO cycle is dominant in the massive star. Massive star, it means mass, a star with a mass greater than the sun by at least 20%. I would like just to observe that the CNO consists of 2 cycles. The first cycle is absolutely dominant, 99.95%, and in that case, neutrinos are emitted by nitrogen 13 and oxygen 15. So what we face is to measure the CNO cycle, but in which way to measure? I think that in the case I've been lucky, because in the sun, as I already said, 99% of the power is produced by the PP chain. It remains 1%, and this 1% is produced just by CNO. So what we started is to measure just this 1%. The measurement was very difficult, first because the statistic was very low, but also because in the region where we measure, we try to measure the CNO distribution, are present also two other things. One is the signal of PAP. Another one is a residue of bismuth-210. For the PAP, you have no problem because you have already measured it, and in any case, it's strongly constrained by the solar luminosity and by the ratio with the PP flux. So, but remain CNO and bismuth-210, which, and if we try to fit them together, the fit return the sum. Then we have to try a method to constrain the bismuth-210. And this method has been found just because in the scintillator there is also residue of polonium-210. Polonium-210, bismuth-210 are produced by lead-210. Lead-210 decay in the scintillator, but the energy of the decay products are below the threshold of the detector. But what is interesting is that bismuth-210 and polonium-210 are in the same chain, and then are in circular equilibrium. It means that the polonium-210 rate and the bismuth-210 rate are the same. But we have a further complication that in the scintillator, we have also the presence of polonium out equilibrium. And what we observe that this polonium out equilibrium increases only any time that we do some operation, external operation on the scintillator. Then what we did is to wait the decay of this outer equilibrium. The half-life of polonium-210 is about 200 days, and then we remain only with a plateau which corresponds to the continuous production of polonium-210 by lead-210. But also here there is some difficulties because there is a fluctuation on this plateau, and then the fluctuation are due to the fact that on the internal walls of the inner vessel there are dust, particulate, and there are lead-210 which continues to produce polonium-210, and this polonium-210 move in the fiducial volume due to the fact that exists in the scintillator convective motion. So what we have to do is to avoid this convective motion and then stabilize the temperature. What we did with a thermal isolation of the detector and also with copper coils on top, I have no time to explain, but we established a top-bottom gradient. And finally, what you succeed is to obtain excellent temperature stability within the probe resolutions. These probe resolutions were installed in the scintillator, in the detector, which arrive at 0.07 degree. This means that at the time we were able to measure the polonium-210, and then the rate of, once measured the polonium-210 rate, it was possible to measure the rate of bismuth-210 because that's the same. And finally, with this constraint, it was possible to fit the distribution, and you obtain the rate of CNO, which was 6.7 plus 2 minus 0.8 coin per day per 100 tons. What is important is that the no observation of CNO was excluded at the 7 sigma confidence level. But this is only one method we use in order to measure as usual. Because what we use also another method which corresponds to the directionality, which is a method developing within our collaboration. This method, scusa ma questa roba qui mi fa perdere un sacco di tempo. Because this method concerns the fact that in a liquid as a scintillator are produced also Cherenkov events. But the problem is in which way does untangle these Cherenkov events, from the hits of the scintillator hits, which, as we know, are emitted completely random. Now, the problem is that the Cherenkov light is emitted instantly, while the scintillator light emission needs some time to decay. The fastest way is 1.6 nanoseconds. Then what we did is to take into account only the one of first earliest hit, and these are the more probable to do Cherenkov. And because, as I say, the scintillator hit are not correlated with the sun direction, the background, the event background produced by, the Cherenkov events produced by background are also uncorrelated, but on the other hand, the signal produced by neutrino signal the neutrino interaction are correlated. And this is just a Monte Carlo simulation of the Cherenkov photon and scintillator photon in a time scale. Okay, we apply this with CNO. And what we obtain is this one, that in black we observe the CNO, the distribution, sorry. Obtain the distribution of the events. These are the Cherenkov events corresponding to one or two first heat emitted, and these are fitted with a Monte Carlo, obtaining what is the background, which is flat, more or less flat, and the signal in the direction of the sun, which has a maximum of 0.7 or 0.7 for cos alpha, where alpha is the angle between the heat and the sun direction. In that case, what you obtain is 7.2 with this error. This is, of course, is not so precise as in the previous case, but is an agreement. And in any case, CNO is rejected at 5 sigma. And this means that this result obtained on CNO is very robust, because with two competing dependent analyses, what you obtain is evidence of more than 5 sigma. Finally, what we did is to put together the two analyses. The multivariate fit with the subtraction of bismuth 10, the constraint of bismuth 10, and the directionality. In this case, these results are the best. We obtain 6.7 plus 1.2 minus 0.7, and no CNO has been rejected as a level 8 sigma. I think I would like to say that, of course, this is a good result, because we obtain after 8 years, we succeeded to validate the hypothesis done by Bethe and von Weizsäcker. But I think that even more important is that in that case, Borexino demonstrated how the star of any size shine, because for the size close to the sun, what was valid is the PP chain. For the star, massive star, what was valid was the CNO cycle. Now is my last result, and concern the tentative to fix the long-standing puzzle between high and low metallicity. This, at the left, we see the result of heliosismology. It was very known that heliosismology differs the low metallicity as a level of more than 7 sigma. And this is on the other hand, the measurement of the neutrino flux, solar neutrino flux. In blue is the low metallicity, in red the high metallicity, in green the result of Borexino plus Kamlan, and this in gray are all solar with Borexino, evident, plus Kamlan. And in that case, I think what you obtain is a low metallicity, this favor at the level 3.1. This means that this, in any case, is strong in favor of the inner high metallicity. Also, if, of course, this is model dependent, because in any case, the metallicity is very strong connected in the sun with the opacity. I have no time to talk on neutrinos, nor of the no standard neutrino interaction, and now I arrive to the conclusion. I think that it was worth spending 22 years on Borexino experiment in order to achieve all this major breakthrough. First of all, an unprecedented radio purity of the scintillator detector obtained for the first time and not obtained for other experiments until now. The measurement of the individual fluxes of neutrino emitting PP chain fusion reaction, the observation of neutrino oscillation in vacuum and the check on MSW LMA model, the first experimental evidence of the existence of CNR cycle, a strong hints in favor of high metallicity, solving the long-standing puzzle between high metallicity and low metallicity. I had no time to talk on geoneutrino, it's a continental crust, and only a few words. Borexino is a unique experiment able to measure the solar neutrinos in this moment. But for geoneutrinos, there is also another experiment, which is a Camlan experiment. Camlan is an oceanic crust, Borexino is a continental crust, and put both together, what we obtain is a good estimation of the radioactivity in the Earth mantle. Okay, these are the institution which in turn has collaborated with Borexino, but normally were no more than 6 or 7 in the same time. And finally, but before to thank you for your attention, I would like only to say that the Borexino legacy is not only the achievement hardware and the discoveries, but also to the fact that I think that is in any case a good example, especially for the young physicist, to be not afraid to face very difficult experiment because sometimes the very difficult experiment are able to produce very good results. And now, thanks to your attention.
Thanks a lot to Giampaolo. A few questions who are separating us from the lunch, but it's time if anyone wants to comment or ask questions for Giampaolo. If not, I think people is hungry. So,
in any case, I have a request to Lincei to have a better system because this was very difficult to use. I lost
this is a lot of request for improvement to the Accademia. Fine. So thank you very much. Lunch break.
Okay, so we are perfect in time, and we start the afternoon session. And this morning we have the description of the two experiments that are Gallex and Borexino, and now we have the implication, let me say. So Professor Smirnov will report to us what will be the impact of this experiment, what we know now on neutrino physics and on the other application. So please, Lincei.
Now it works, okay? So this is the longest title of my talk I gave ever. Okay. And in the next slide, you will see my interpretation of this title. So this is my beloved, okay, works. So what I will talk about is solar neutrino problem and its solutions. Then I will briefly explain what is this neutrino flavor conversion and MSW effect. Then this is the main part of the talk, I will say what is actually implication of Gallex. And so the main stuff is that it played fundamental role in identification of possible solutions and some kind of discrimination. And then Borexino, which provides a confirmation of LMA and put bounds on new physics beyond LMA solution. This is a short story of solar neutrino problem, and what was kind of unusual that solution of the problem was provided even before the problem was really established. And what is solution? Solution is explanation of deficit of argon production in home stake result. And so in attempt to explain this, a number of solutions have been invoked, and signatures and smoking guns of these solutions already were done and explicitly explained before even experimental data appeared. So we had a prediction for forthcoming and possible future experiments, and interpretation of the experimental results was almost immediately, because kind of theory was prepared already to all possible versions of the outcome. So, and conclusion was in terms of favored, disfavored, or excluded solutions of the solar neutrino problem, or exclusion of some range of parameters. So actually, the establishing of solution was a process of identification or selection. This is like a quiz. You know, you have a number of possibilities, and you need to select among these possibilities. And I should start, of course, with Bruno Pontecorvo, which I think is the father of the problem. So he actually invented the method to detect solar neutrinos. He introduced neutrino oscillations in 1957 and 58, much before the data from home stake appeared. And actually, he predicted possible deficit of solar neutrinos due to oscillations on the way to the Earth. So in 67, before the data were released, he said that if oscillation length is large, from the point of view of detection possibilities, an ideal object is the sun. So Ray Davis has observed a deficit 1/3 1 year later, and it was already questioned immediately what is the origin of this deficit, and there were solutions based on astrophysics, nuclear physics, and neutrino particle physics. What was important that Davis has observed the time variations of the signal, which are in anti-correlation, as he claim with 11 years solar activity, or sunspot number, which implies actually existence of a large magnetic moment of neutrino, which flips in the magnetic field of the sun, which actually varies with 11 years period. Well, actually, Davis believed in this magnetic field, his variations and magnetic field explanation till the end. In 1998, in final publication of home-stake result, it was not even citation of MSW paper. So he thought that he observed the deficit, and explanation is large magnetic moment of neutrino. Another important actor in this game is George Zatsepin, who actually put forward the program of neutrino spectroscopy, measuring of neutrino fluxes of different types, but he thought about radiochemical experiment, something which is extension of home-stake result. And so the idea is the program of a series of such experiments with different thresholds. And in this framework, Kuzmin has proposed gallium-germanium method. Also lithium, beryllium, and George Zatsepin was a part of SAGE experiment. So this is the catalog of solutions which appeared soon after deficit has been observed. So among them is vacuum oscillations averaged. Actually, Pontecorvo also discussed average oscillations. And in fact, PP neutrinos are precisely undergo essentially vacuum oscillations. So bulk of solar neutrinos actually undergo what Pontecorvo was thinking about. Then neutrino decay, neutrino spin precession in magnetic field, then resonance oscillations in matter, then just so oscillations suggested by Glacio and Krauss, then resonance spin flavor precession in matter, and then MSW effect with some off-diagonal, what we call now non-standard neutrino interactions. So there is a set of solutions, and the problem was to identify what is correct. Now, the process of selection was the following. There were these pioneering experiments after home-stake, Kamiakande, SAGE, and Gallex. So they reinforced the problem. Astrophysical solution after results of these experiments were disfavored and nearly excluded. Then energy dependence of the effect behind this deficit showed up, so weaker suppression has been observed in home-stake experiment in Super Kamiakande and also in gallium. Significant time variations of signals were not observed in other experiments rather than home-stake. Some discrimination of solutions already were performed, and then the three MSW solutions were coined, which is small mixing angle solution, large mixing angle solution, and low solution of the problem. So 1998 was the year of big turn after Super Kamiakande result. So not only Super Kamiakande has observed and confirmed solution of the atmospheric neutrino deficit by oscillations with nearly maximal mixing, which actually played an important role because it actually removed the prejudice that small mixing angle should be the solution of the solar neutrino problem. There were two key observations by Super Kamiakande. One is the flat spectrum of events, and there is no significant distortion. So Super Kamiakande was sensitive to boron neutrino part. So the regional spectrum was known, and the analysis showed that there is no distortion of the spectrum, at least with accuracy they had that time. And then another important point, there is no day-night variations of the signal was observed, which actually was predicted by some of the solutions. So we made an analysis of the data with John Bacall and Plyman Krastev and published two probably relevant papers. One is 98, which kind of summarized what has been done essentially before Super K, and with some results from Super K. And in 99, we have published the paper, is LMA MSW solution of the solar is the solution of the solar neutrino problem. So large mixing angle solution already in 99 was kind of favorite one, and others disfavored. So this is the plot from this figure already for large mixing angle solution region. So this is sine squared to theta. This is delta m square, and you see this is where large mixing angle solution is. So these blue contours are with just rates analysis, and adding the day-night results, so negative, actually gives, shifts this slightly upward with this best fit point. And now the best fit point is somewhere here. So also we computed this possible energy distortion, and you see here so the predictions and then experimental data that time. So we conclude that recent results on solar neutrinos provide hint that LMA MSW solution could be correct. And so 2002 is Annus Mirabilis. Actually, this title was suggested by Eligio Lisi, and I gave talks in Venice. And actually, it was some conference here organized by Mila Baldacci, kind of summarizing this enormous progress during these years. Two important events. The SNO has published results on both charge current and, more important even, by neutral current. So they do not see any deficit in neutral currents, which tells us that electron neutrinos are transformed in muon and tau, because neutral currents do not change when you have such transformations. And then the same year, essentially, the Kamlan has published the first results of oscillations of reactor neutrinos. And oscillation parameters extracted from this experiment coincide with what is needed for LMA MSW solution. So you can turn the things and say, okay, suppose we just performed Kamlan experiment without any solar neutrino experiments. So we measured parameters, and then we can compute what you expect for solar neutrinos, and you will reproduce in this way LMA solution. The only what Kamlan cannot do, distinguish between transition to sterile neutrinos or active neutrinos. And that's what actually provided by SNO result. Well, other mechanisms since that time becomes disfavored and at most subleading with respect to LMA. Let me say a few words about resonant flavor conversion, or MSW effect. I think this is the shortest way how you can get really very precise results in spite of kind of very schematic picture. So Wolfenstein has first considered scattering of neutrinos and refraction of neutrinos in medium. Well, actually, he was not the first, but he was the first who computed really all these potentials or refraction indices. So he discussed the oscillations of massive neutrino, not only massless but also massive neutrinos with standard potential. He introduced evolution equation and have written Hamiltonian of evolution. Interestingly enough, he concluded in his paper, famous paper, that this has no implications for solar neutrinos. And this is because he thought because of adiabatic conditions inside the sun, and therefore adiabaticity doesn't produce any effect. So you have some state, and then at the end you will have again the same state. Now, the key notions here are the eigenstates and mixing in matter. So we have flavor states, and I explained this using two neutrino oscillations, say electron and muon neutrino. So we have Hamiltonian in vacuum, and mass states are the eigenstates of this Hamiltonian. Mixing angle in vacuum connects flavor states with mass states. Now, in the case of matter, we should add to the Hamiltonian the term which describes interaction of neutrinos with medium, this refraction effect or the potential. And of course, with this, the eigenstates change. They already differ from what we have in vacuum. So we have two new states, which is nu1m and nu2m. And now the angle which connects flavor states with these eigenstates in medium is the mixing angle in medium. Okay, so since V, the potential depends on number density of particles, and this vacuum term depends on energy, then mixing angle and medium start to depend on number density and on energy. And so this is the example of what's going on. Suppose you have eigenstate nu2m, which is at high densities is essentially electron neutrino state. Right, so mixing angle determines here, it determines flavor composition of eigenstates. So you have this connection in both directions. Now, if the state propagates to the lower density, then at some density, then the mixing angle changes because density changes, mixing angle changes. At certain density, you will have equal number of, say, electron flavor and muon flavor, and this is the resonance situation. And then you go further and you have the situation when what you have in vacuum, so that this state nu2m mainly muon neutrino and less electron neutrino in this state. This is resonance, which means that mixing angle parameter sine squared to theta m has the resonance dependence on the number density and on energy of neutrinos. And here you see the situation with 1,2 mixing, and this is with 1,3 mixing. This is 0 density, and so this semi-plane corresponds to antineutrinos, and this is to neutrinos, and you see two resonances are in neutrino plane. So the resonance is when vacuum oscillation length coincides with refraction length, which is inverse of the potential. Essentially, this is self-frequency of the medium. Now, in other terms, this resonance condition is written here, that potential is delta m squared over to energy cosine theta. The width of the resonance is proportional to tangent to theta. So if you have small mixing, then the resonance is sharp. Now, this is 0 density, and the mixing angle in medium coincides with vacuum mixing. Now, this is the resonance when mixing angle is pi over 4. And at very high densities, the mixing angle converges to pi over 2. I think this is what we need to know then to come to really what's going on inside the sun. So neutrinos are produced in the central part of the sun. Then, according to LMA solution, they undergo adiabatic conversion inside the sun. And I will explain what is this. Then, from the surface, actually even from some inner parts of the sun to the Earth, the coherence is lost, which means that the oscillations are averaged, the eigenstates start to propagate independently, and there is no oscillation effect. Then what arrives at the surface of the Earth are mass states. So not flavor states, and mass states. In medium, mass states oscillate. So you will have so-called regeneration effect inside the Earth. So nu1 and nu2 start to oscillate, reproducing or increasing the number of electron neutrinos. And this is the origin of so-called day-night asymmetry, so which means that during the night you will see a bigger signal in electron neutrinos. Now, this is the situation with PP neutrinos. Essentially, they have oscillations in vacuum. In this case, electron neutrino is described by two wave packets. So-called propagation of electron neutrinos is described by two wave packets, which correspond to nu1 and nu2, right? So we have mixing, we have expansion of electron neutrino into nu1, nu2, and therefore propagation is described by two wave packets. So there's a latent presence of muon flavor already in electron neutrino state. Because according to mixing, this nu1m and nu2m, they have also flavor compositions. So they partly correspond to have an electron neutrino component and then muon neutrino component. And the same is here. Now, when you produce electron neutrino, these green parts, which correspond to muon neutrino, they cancel each other because some additional minus sign in the mixing scheme. And therefore, you see electron neutrino. However, once the system starts to propagate, and you have additional phase shift, already you will have no cancellation between muon parts here and there, and therefore you will have appearance of muon neutrino. So this is what happens. You have phases of nu1 and nu2 in initial state, but then during the propagation and due to difference of the masses of these states, you will have phase shift. You have first this one, then that one, then you will have something like this. And in your originally produced electron neutrino state, you have appearance of muon neutrino. Now, this is adiabatic conversion. Suppose you start with large density. If you have large, but not very large density, you have nu1m and nu2m. So again, as it is described before, was described before. Now, if density changes slowly, then derivative of mixing angle is small. It's much smaller than splitting. So these are eigenvalues. So but this is important. Derivative of mixing angle is some dynamical characteristic. It tells you how fast the density changes. If density changes very slowly, then you have such conditions. And under such conditions, there is no transition between eigenstates, nu1m and nu2m. So what's going on is when this system propagates, the sizes of this wave packet, the amplitude, they are conserved. And the only what is changing, the flavor of these states, according to change of the mixing angle. Density changes, mixing angle changes, and therefore flavor content of eigenstates change. You start from this, and you end up by this, where you have dominant, say, muon component. And this is how your original electron neutrino is transformed, or at least partially, to muon neutrino. I haven't discussed these oscillations, because in the case of solar neutrinos, they are irrelevant. So they anyway are averaged out. And so these wave packets will essentially propagate independently and arrive at the Earth. So you just need to compute moduli square of these amplitudes and sum up, and then you will get final result for your survival probability. Now, this is the case of so-called non-oscillatory transition. The picture before corresponds to so-called transition region. I will show you later, and also you saw this in the previous talks. So there is a vacuum oscillation, essentially dominating at very low energies. Then there is a transition region, and then there's transition to so-called matter-dominated situation, a regime. And this is what happens. If you start with very big densities, or you have high energies, then your state, electron neutrino state, essentially coincides with nu2m. Okay? And so it's essentially red, everything. And the second eigenstate can be neglected. Then this stuff propagates, and it propagates adiabatically. Therefore, the amplitude doesn't change. The size of the amplitude of this wave packet doesn't change. And so what's going on is your nu2m is transformed to nu2, which is the eigenstate in vacuum. And so you can immediately compute what is the amount of electron neutrino. So this is sine theta, and you square this, and you get this famous result that the survival probability in such a situation is just sine square theta. So whole evolution is just transformation of nu2m to nu2, and change of the flavor composition of these eigenstates. Now what's going on the way from the sun to the Earth, and actually partially already inside the sun, is that the coherence is lost, which means that if you start from such a situation and your wave packets overlap, then after some propagation you have already not overlapping wave packets, and therefore there is no oscillations. And they interact with your detector independently. So you need to compute first interaction of one of these wave packet, compute the probability, then compute probability from the second one, and sum up these probabilities. So this is how the physics looks like. So this is whole kind of scheme of the transition. You produce electron neutrino, you decompose this into nu1m, nu2m, nu3m, and this is determined by mixing angle at the production point. So mixing at the production point determines for you amount of these eigenstates. Then they propagate independently. First, inside the sun, say nu1m go to nu1, nu2m go to nu2, nu3 to nu3, and you have loss of the coherence. And that is continued from the sun, surface of the sun and the Earth. So what arrives at the Earth is nu1, nu2, nu3. And then you need to compute the probability that nu1 oscillates and eventually has a nu-e. And the same is for nu2 and nu3 independently. And then sum up the probability. And then you get this immediately result for survival probability. I don't want to discuss and go into details, but this is so simple. And the precision is 10 to the minus 6. So you should not worry about any corrections. This simple scheme already determines your probability with so high accuracy. Oh, so that's there's something problem. So if you are during the day, then these probabilities here are just given by mixing angle in vacuum. During the night, you really need to compute the probability of oscillation of nu1, nu2, and nu3 inside the Earth. Now, this is what happens with oscillations inside the Earth. Probably I will just keep this. You need really to compute how nu1 and nu2 oscillate, because nu3 essentially decouples, and then nu1 and nu2, you compute this probability of nu1 go to nu-e and nu2 go to nu-e. This is actually what you get when you compute day-night effect. So this is zenith angle distribution of the events. So this is during the day, and this is during the night. And so this line corresponds to 3% day-night asymmetry. This was actually claimed in the initial publication of Super Kamiakanda, and this is 4.2%. So these were the points. You see big spread. But anyway, so the original result was 3.3, and now it is less. And I will discuss this a little bit later. Now let me go to Gallex and identification of the solution. So I should say that, in fact, collaboration have both Gallex and Sage, they have published papers on implications. And in fact they provided very precise and detailed study of what are implications of the results. So I agree completely with what they are saying. And in some sense, I will repeat what you can find in the papers. So already first Gallex result, and it was already in Till Kirsten talk, at 2 sigma level disfavored so-called astrophysical solution. So one of the merit of Gallex result is essentially disfavoring or excluding eventually the astrophysical solutions. And that was kind of the first step in selection of different solutions. So one can use also this luminosity constraint, so you can find what is pp neutrino flux from this constraint, and you see that it's kind of on the border of exclusion playing this role. Now, so it was extraction of pp neutrino flux, which Till has discussed in details. And what has been observed eventually that even pp neutrino flux is suppressed, and the probability has been extracted, and the probability is something like 0.55 or 0.52, which corresponds to vacuum oscillations with large mixing angle solution. Now, this is conclusion from their paper of 92. This is by later. By 1997, Gallex established both the presence of pp neutrinos and a significant deficit in sub-MeV range. So this was the strongest indication for neutrino transformations on the way between the solar core and the Earth, implying non-zero mass. So probably I may not agree with that implies a non-zero neutrino mass. Still, by that time, for instance, solutions based on spin flip existed, or solutions based on non-standard neutrino interactions. That takes some more time to exclude those solutions. Now, what else? In fact, Gallex has disfavored neutrino decay and also disfavored strong time variations of the signal observed by home-stake result. This is important plot, actually again from this 92 paper, and what you see here is so-called MSW triangles in the sine square 2 theta delta m square plane. And you see here home stake band, and Gallex band is shifted because of different energies of neutrinos, effective energies detected by Gallex and home stake. And that actually allows to pick up the regions of overlap. And you see here 3 regions which correspond essentially to small mixing angle solution, large mixing angle solution, and low solution. So this is more statistical elaborated situation. Low disappears here. This is excluded regions, and this is what we call a small mixing angle, and this is large mixing angle solution. So these are how the suppression probability looks like for different solutions. For a small mixing angle, it has this very strong suppression in a certain range. So this is a probability as a function of neutrino energy. This is for LMA solution. You have here you have vacuum oscillation, essentially. So this is not logarithmic scale, so you don't see. And so this is transition region, and this is the region where you have these so-called matter-dominated non-oscillatory transformations. And 2 lines here correspond to signal during the day and during the night. Now, this is for low solution, which eventually Borexino has excluded, so also excluded. This probably I will not go into details. Essentially, this is procedure of subtraction. You can take a gallium result and subtract what you measure already, say, by super Kamiokande or Kamiokande, and then what is left essentially for PP neutrino and beryllium neutrino, which give the biggest contribution, and therefore you can compute what it should be suppression to explain the signal. And you see what they extracted is 0.50, 0.556. This when they extracted only boron neutrino flux, and this is when they also used a result from Borexino and extracted beryllium neutrino contribution. And so these are the probabilities, which is essentially the same what you get from LMA solution. Well, probably I skipped this. It was kind of debate on possible time change of the signal in gallium. And if I have time, I may some comment what could be behind this if we believe in this change with time. Now, Borexino. So after identification of LMA MSW solution, what is left is the following. So next goals are check of the solution, precision measurements of parameters, study of 1-3 effect in solar neutrinos, searches for possible deviations from LMA MSW solution, and bounds on new physics. Well, other proposed mechanism can produce only sub-leading effects, like, for instance, spin flavor precession, oscillations to sterile neutrinos, non-standard interaction. And actually, these are the topics of very intensive studies now these days. So looking for sub-leading effects on the top of LMA solution. So this already Gianpaolo has shown for us exclusion of low solution on the basis of only Borexino result. So here is a profile of LMA solution, dependence of probability on the energy for 2 different delta m squares. One is what is extracted from solar neutrinos, and this is if you use parameters of Kamland result. So at low energies, we just have vacuum oscillation, essentially, effect, and this is described by this usual formula. At very high energies, all these lines are converging to this non-oscillatory transition, sine square to theta. So we have vacuum-dominated region here, transition region, and then matter-dominated region in this case. So let me say a few words about tension, which actually was kind of hot topic for, say, last 10 years. So you start to look now in more details on this zoomed LMA solution and try to find if there are already some stuff which cannot be embedded immediately in the simple solution. So one thing is that actually Super Kamiokande and SNO have not seen the upturn of the spectrum, because with decrease of energy, suppression should become lower, smaller. The second one is quite large day-night asymmetry observed by Super Kamiokande, and this actually leads to different values of delta m squared 2, 1 extracted from solar neutrino data and from CAMLAND. It's like in one case you have 7, in other 4.2, and that was a bit more than 2 sigma disagreement. Now that may actually testify that actually real potential is 1.6 times larger than what Wolfenstein's standard potential gives. And then people were excited that maybe you have non-standard interactions effects which contribute to the potential. And in fact, such solutions of this kind of small subleading problem have been provided. Another thing which actually bothers me even now, so if you take an LMA solution with parameters, best fit parameters, you predict for home stake result more than 3 SNU, while home stake observed 2.5 SNU. Again, this agreement is something like maybe 2.2 sigma or something like this. But it is kind of persisting disagreement. If you want, I can elaborate. So this is something strange. And the conclusion is that probably something happens in this transition region between matter-dominated and vacuum-dominated parts. So it's tied. Huh?
Doesn't work.
No.
No.
So, and people jumped on this problem, starting to invent new additional mechanisms to explain this tension, and using this intermediate region where we have no real probe. So experimental data are mostly in low energy part and then in high energy part. And there's a gap in intermediate way. So apart from non-standard interactions, and I will show you the plots, non-standard interactions, so we proposed, for instance, existence of additional sterile neutrino, very light sterile neutrino, which is lighter than the second neutrino, somewhere here. So this is the total spectrum with 4 neutrinos. And that produces additional deeps. So if you have just LMA, you would expect something like this, dependence of survival probability on neutrino energy. With this additional neutrino, with small mixing and with small masses, you may have something like this or something like that, depending on parameters, depending on the mass of this additional neutrino, and depending on the mixing. So in this way, you can reproduce the following. So with sterile neutrino, you have this green part for certain parameters, instead of this blue, which is just LMA solution. So you have here the dip. You do not change much here. Of course, you will suppress upturn. Instead of going up, you have flat here. And so in this way, you also can suppress the day-night asymmetry, just solving the problem. And you see here also the lines which correspond to different non-standard interactions. Again, you can flatten spectrum here and produce additional suppression at low energies. So this is another suggestion, refraction due to very light mediators. So you have additional interactions, not usual this NSI, which imply heavy mediators, but here is with light mediators, and again you can get such a dip. Now, this is a famous plot from Borexino. At least there is no hint that something wrong happens in this intermediate range. So PEP is not very strongly suppressed. It's not like here. Also, the error bars are still big. I'm wondering CNO neutrinos can contribute to this. Still, of course, you have big uncertainties in the produced fluxes, but still you may probably compute what is the probability of, or at least range of suppression probabilities for CNO. So we have here perfect agreement with MSW LMA, and this what purely, say, Pontecorvo solution would give for you if you have just vacuum oscillations everywhere. So fortunately, these tensions start to evaporate, and although there is no official publications, super Kamiya candidate seems see now lower day-night asymmetry, something like 2%. And now the agreement between solar neutrino extraction regions and CAMLAND is quite similar, something like 1.2 sigma. So practically this disappears. And another thing that now it seems that super Kamiya candidates start to see upturn of the spectrum at low energies. Now what's next? So what we can do, and in fact, Borexino is a very nice machine because with LMA identified solutions and with more or less known fluxes of solar neutrinos, you can use these solar neutrinos as kind of known beam which you can use to explore new physics in your detector. So you have beam and you explore some new interactions which occur in your detector. And there is a series of studies and a number of papers on this. So you have this neutrino flux at the detector, you study interactions, and you can restrict magnetic moment, non-standard interactions, interactions with light mediators, etc. In some cases, you need to come back and recalculate solar neutrino fluxes because these new effects can affect also these produced fluxes. And this is the game which people are playing now. So this is a standard set of possible physics beyond the standard model and beyond LMA. And Borexino has contributed to some of the studies. And let me just briefly flash what has been done. Here you see the bounds on non-standard neutrino interaction. And Gianpaolo has shown already, or had no time, but now, now I'm showing this. So you see, this is epsilon. This is parameter of non-standard interaction with respect to standard interactions. So you see it here, they have bounds. This is the red one. So first, they are better in certain regions than other bounds. And so this non-standard interaction here is, for instance, should be below than 0.15. And here is even stronger. So this is that set from Borexino 2. Now, they put also bound on the magnetic moment of neutrino, because if you have big magnetic moment, then you have additional contribution to scattering of neutrinos from the sun on electrons, and that produce additional effect at low energies especially, and that allows them to put this bound on effective magnetic moment of neutrino. And this is important because that restricts some subleading effects, for instance, from the spin flavor precession. So they put also bound on antineutrinos from the sun, and you see Borexino gives actually quite strong bound, stronger than SNO and super Kamiya candidate. And again, this is important to restrict so-called spin flavor precession, because when you have this spin flavor precession, what happens is that electron neutrinos go to, say, muon neutrinos, and muon neutrinos go to electron antineutrinos. In this way, you produce electron antineutrinos, and you can search for in this experiment and put these bounds. So this is important also to restricting this spin flavor precession as a subleading effect. So this is this is very kind of recent paper on various these additional effects. And you see how these effects change the spectrum. So this is the standard. So this actually a count with respect to what you expect. And with these new effects, you have strong change of the energy spectrum of events, essentially. This is number of hits on this axis. And they studied vector interactions, non-standard interactions, scalar and pseudo-scalar interactions, and also the magnetic moment. So let me come to my conclusion. Gallium-germanium experiment played fundamental role in the process of identification of solution of the solar neutrino problem. It actually motivated, together with other experiments, the Camland. So the established MSW solution, LMA solution, is based on adiabatic flavor conversion driven by change of the mixing angle in matter with density. Borexino has provided important checks of LMA MSW solution, in particular conforming the energy profile of the effect in whole energy range. So this is whole spectroscopy, full spectroscopy of solar neutrino using new E scattering. So all the components of the solar neutrino flux were tested. Well, Borexino produces bounds on beyond the LMA effects. And actually, all this opens a new phase of studies of astrophysics of the sun. Thank you.
So thank you, Alexei. We are perfectly in time, so that's, there are room for some question and observation.
I just want to make a remark, just a remark. For those who do not know, the S in MSW means Smirnov.
Okay, so here in the first row, Gianpaolo.
Yeah.
Gianpaolo is asking. Yeah, thanks.
Okay, I would like to say a few things. One is that for what concerns the NSI, no standard neutrino interaction, what we have shown is our first analysis done taking into account only the diagonal members. Now we are doing a second analysis using all the parameters, also out of diagonal, but also with more statistics and with a lower background due to the krypton 45, which is one of the most dangerous. And then, okay, we hope in October to have some better data.
Okay.
For the other things that you mentioned, is true. I had no time to show that also for the magnetic moment, neutrino magnetic moment, and for the search for antineutrinos from sun, we had good limits. Okay, but it's they already published.
Yeah. Okay.
And finally, I would like to say, for what concerns because it's a problem remaining, in my opinion, for not only my opinion, but for the oscillation, it's just the intermediate region. Okay, there is some, they can change or due to NSI, surely. But also, I remember that some years ago, we proposed also something of the existence of the sterile neutrino, which can, in some way, change the shape of this. That is true?
I'm not aware about your suggestion. So we started to do this with Pedro de Holland. I think the first suggestion was in 2004 or 2006, and then we had another publications in 2011. This is what I'm showing here.
So I miss this. Okay, thank you.
Okay, there is another request.
Yes, I have a comment and a question. The comment is about Camland. So you said that with respect to solar neutrinos, it cannot distinguish active and sterile oscillations. I would like to say that in addition, it cannot distinguish the octant. So matter effects are crucial to know that sin squared theta 1,2 is 0.3, not 0.7.
Sure. Yeah, right.
And the question is about the time, the sequence of data of Gallex in time. So you said there could be an explanation of this variation, but maybe I missed. What did you mean?
Well, can you switch to my slides? Because I have additional slides after. So it's like
I'm curious to know about
it's like after dinner talk. You know? Can you?
Possiamo rimettere le slide?
So, actually, this is the question of nature of neutrino mass,
Okay,
not nature
we have
of
slides.
Yeah, so not nature of neutrino, but nature of a neutrino mass, and so which means that what is really behind the mechanism of generation of neutrino mass? We think that it probably seesaw, but even seesaw is kind of more complicated stuff. You need to have two interactions with usual Higgs field, and then you need to produce mass of sterile neutrino, which may have also some funny properties. But it may happen that neutrino mass is generated not by vacuum expectation value of scalar field, but by scalar field. So instead of just vacuum expectation value, you have scalar particles, like dark matter, composing dark matter. And then essentially effect is quite similar to what we have with vacuum expectation. Well, neutrino propagates in this background, and it acquires the mass. Precisely like particles acquire the mass in the standard model, propagating in the vacuum expectation value. Okay? Now, if you have this scalar field, and if you have very big density, which you actually need, then that has classical properties. This field acquires classical properties, and in particular, it may have oscillations like just oscillator, classical oscillator. So your field, classical field, which couples with neutrino, has these interactions, and that produces. Okay, so this is the way how it may change. So time dependence. Actually, the time dependence is determined by the mass of this scalar particle, and yeah, then you can expect some time variations of the signal. Another suggestion is that what Dwali, what Chaspati are suggesting, that if neutrino mass is generated by condensate of neutrinos themselves, so neutrino pairs acquire the vacuum expectation value. And you have some phase transitions in the universe. You have a set of, say, strings in the universe due to symmetry violation due to this condensate. And then if you move close to these strings, mixing angle changes. Masses are changing. So, and interestingly enough, so they made an estimation, and the period can be of the order of, say, 10 years. So you may expect during 10 years, if same string is coming around us, or so the Earth is moving in this network of the strings, then neutrino change their properties, mixing angles. So this is what I'm saying, the first. So maybe it's too premature to think that we know what is the nature of neutrino mass. And one needs to explore properties of neutrino mass, namely, it's possible energy dependence, and it's possible time dependence, and it's possible dependence on the situation, if we are here or in the center of galaxy or in intergalactic space.
Okay. If there are no very urgent questions, I think that we can stop here. Thank you again. Lincei. So we have a coffee break now, and we return back in 15 minutes. Scusate, qualcuno ha chiesto un taxi per le 17 da qui o... Perché non si sa chi sia, cioè, giusto perché... Ah, Stefano. So, see? Okay.
Hello?
Yeah, and we are ready to restart. There is the talk of Professor Axton that is in connection from remote. So I leave to him the start of the presentation on the astrophysical implication of the understanding of the sun and the stars. So please, thank you. Are you
Great.
connected? Is okay?
I think so. Shall I just share screen?
Okay. Perfect. You can start your presentation.
Okay. All right, let's see here. Does that appear to be in full screen?
It is not in full screen. You have to
Okay.
start play.
Okay, there we go.
No. Okay. Perfect.
Yeah, first let me apologize for not being able to be there in person. I was so much looking forward to this meeting and seeing some old friends that I haven't seen in quite a few years. But things are what they are. So I prepared a talk that is kind of a historical that tries to follow the development of the standard solar model as the neutrino field progressed. I'll talk about the early days, and then particularly the roles of Gallex and Borexino in that development, and also say a little bit about the remaining opportunities that we have today. In the early days, the 1946 Bruno Pontecorvo first suggested that neutrinos, and he was actually thinking about reactor neutrinos, might be observable based on a reaction on chlorine-37. This was followed up by Louis Alvarez, who actually did a very serious study of this process for many years. And who actually proposed chemical methods for extracting argon-37 from organic fluids. These studies were done before parity violation was discovered, and at a time when there were suggestions later retracted that the neutrino might be a Majorana particle. So it was then possible that antineutrinos would generate the transition from chlorine to argon. Finally, Davis mounted a 3.8-ton cleaning fluid detector at Brookhaven. He buried it 18 feet underground to get rid of at least most of the hadronic cosmic ray backgrounds. And the first limit he placed on the solar neutrino flux was an amusing 40,000 SNU, assuming the sun generated its energy from the CNO cycle. Although Alvarez actually thought about solar neutrinos, detecting solar neutrinos, the expectation at that time was that the sun probably operated on the PP1 chain. And that chain ends with, produces only one neutrino, and it's below the threshold for the chlorine to argon transition. So it didn't appear that this detector was really relevant to seeing solar neutrinos at that time. Things changed in 1959 by a laboratory measurement of reaction rate by Holmgren and Johnson. The rate for helium-3 plus helium-4 had originally just come from theory, been estimated. The measurement that Holmgren and Johnson made yielded a cross-section that was 1,000 times larger than that was being used. And so it was immediately realized that this would feed higher energy branches of the PP chain. At that, Willie Fowler recognized immediately the implications of this. for the chlorine detector. John Bacall had just spent his first postdoctoral year at Indiana working with Konopinski, and one of the problems he dealt with there was electron capture in stellar plasmas. So in 1962, Willie recruited John to join the Caltech stellar modeling group, which already included Eco Even and Dick Sears. And the goal of that effort was actually to create the first quantitative numerical model of the sun, one that would be able to predict the core temperature profile. So John computed the neutrino fluxes offline from that profile, and the result was 1 capture per day for 100,000 gallons of C2CL4. The experiment appeared at that point to be very challenging given the capture rate. The capture rate had actually been estimated based on the known strength of the transition from the argon 30 to the argon 37 ground state. This was known because of the electron capture, a lifetime of argon 37. John gave a seminar in 1963 at the Niels Bohr Institute, and Ben Modelson was in the audience. And when this point came up, Ben pointed out that the potential importance of excited states in argon 37, including in particular the model-independent transition to the isobaric analog state. John then immediately built a little nuclear model of the excited states, estimated the contribution of the excited states, and came to the conclusion that they would increase the cross-section by a factor of 20. Based on his previous calculation, it then gave a capture rate of between 20 and 60 SNU for the chlorine detector, which made it look practical. He also realized that there was a way of validating his prediction, which was the then unknown lifetime of calcium 37, which is the isobaric analog of chlorine 37. So the transitions from chlorine to 37 to argon 37 are all analogous through isospin symmetry for the transitions to 37 calcium to potassium 37. So if his cross-section neutrino absorption cross-section on chlorine was right, then his prediction of the lifetime of calcium 37 should be right, which at that time was not known. And so he predicted that cross-section, and it was subsequently measured by 2 groups. And the agreements agreed with this calculation to about 20%. So this really validated this estimate of a much larger capture rate on chlorine 37. As a result, in 1964, Bacall and Davis published 2 back-to-back papers in PRL arguing that solar neutrinos can now be measured. In 1964, Homestake agreed to host the experiment. The cavern was completed 2 years later at the 4850 level of the mine. The still containment vessel was fabricated in Chicago, shipped in pieces to Homestake, and then finished underground by the miners in 1966. The C2CL4 was brought to the mine in 10 railway car tankers, which were then unloaded and brought underground by hoist in small batches. The first results from the experiment were announced in 1968, an upper bound of about 3 SNU. And the theoretical prediction at that time had been revised and improved. It then stood at 7.5 plus or minus 3 SNU. So this really began to focus attention on the credibility of the standard solar model. It was understood that the neutrinos that Davis were measuring were the very temperature-dependent high-energy solar neutrinos, and therefore the most plausible solution of the problem was just that there was still a factor of 2 uncertainty or so, maybe 3, in the standard solar model. So what is that model? It's really the origin of solar neutrino physics is the desire to test the model of low mass main sequence stellar evolution. How do hydrogen burning stars actually evolve? And the input physics is really relatively simple. It's the assumption of local hydrostatic equilibrium, that there's always everywhere in the star a balance between the gas pressure gradient and the gravitational force. That there's energy generation by hydrogen burning, conversion of 4 protons to helium-4. In the sun, 99% of that burning occurs through the PP chain and 1% through the CNO cycle. There's energy transport by radiation in the interior and by convection in the envelope. And there are various boundary conditions that have to be imposed, including today's mass, radius, and luminosity. When you actually implement this physics, you require lots of microphysics input, including an electron gas equation of state, cross sections for the very low energy nuclear reactions that are needed in the PP chain, some model of the radiative opacity, and some means of fixing the composition of the sun at its birth at zero-age main sequence, including the ratio of hydrogen to helium to metals. So this model describes 70% of the stars in the Milky Way, and it remains really critical to lots of issues in astrophysics, including modern surveys like those of the ESSA's Plato mission coming up in a couple of years. Our picture of solar contraction and evolution actually impacts the standard solar model. The sun forms from a contracting primordial gas cloud. It passes through a phase called the Hayashi phase, where the gas is cool, opaque, has a large temperature gradient, and is contracting. And those are conditions under which the gas is convective and therefore mixes. The radiative transport only becomes more efficient at the star's center when the sun begins to form. And therefore, the sun grows its radiative core from the inside out, beginning a completely convective star and then gradually building up the radiative core until today it comprises 98% of the sun by mass. It takes about 30 million years for this convective core, for this radiative core to become fully mature. And at that point, during this period, the nuclear burning becomes a dominant source of energy for the star. Because of this Hayashi phase mixing, it's always been assumed that the protosun is therefore homogeneous, because this mixing would have smoothed out any inhomogeneities in the gas cloud. The sums of the composition, the hydrogen, the helium, and the heavy elements, of course, must equal to 1. The relative metal abundances are taken from a combination of photospheric measurements and meteoritic measurements. The total amount of metal is fixed to surface abundances after corrections for diffusion. And finally, the unknowns, the remaining unknown, which is the primordial helium abundance, and the mixing length, which is used to describe the base of the convective zone, those are adjusted to produce the present-day solar luminosity and radius in standard models. The result actually is a pretty interesting model. It's dynamic and evolving over the 4.6 years of solar lifetime. First, there's 44% luminosity growth predicted over that period. And this has some really interesting implications for paleoclimate, since if you take a modern model of climate and change the solar constant by about 5%, the oceans freeze. The boronate neutrino flux is amusingly rather a contemporary phenomenon. It has a scale height of about 0.9 billion years. So a billion years ago, it was much below current contemporary fluxes. And there's some really interesting pieces of physics that emerge from this model concerning compositional gradients that are established over time. Over about the first 10 to the 8th years of burning, all of the core's carbon and a bit of its oxygen is burned to nitrogen via the CN cycle. So that's prior to establishment of the CNO equilibrium. And this burning is violent enough to drive early convection of the core. The central core's helium-4 mass fraction increases over its lifetime from 0.27 to 0.64. And that's something one can exploit in building non-standard models to try to smooth out that steep growth. It has a steep gradient in helium-3. Helium-3 is both produced in the PP cycle and consumed, so it's sort of like a catalyst. And this gradient is really interesting. It increases with radius. It extends over an increasing fraction of the core as the sun evolves. And then there's slow diffusion of helium-4 and metals toward the core, reflecting the fact that they have a smaller charge to mass ratio than protons. And this actually has an observable effect on helioseismology. So the model predicts today's core temperature, which is the most important parameter that we can use to check our understanding of, with neutrinos, to check our understanding of that sun. So the three cycles, the PP1 and PP2 and PP3 cycles that make up the PP chain, have this well-known temperature dependence of 4, 11th, and the 22nd power. And so it's known very early in the discussions of the chlorine experiment that if you could measure the boron-8 neutrinos quantitatively, you could deduce the core temperature of the sun to an accuracy of just 1 to a few percent. The chlorine experiment measured primarily those high-energy boron-8 neutrinos, and because of that, there were several dozen solar model solutions to solve the solar neutrino puzzle made in the early 1970s. Almost all of these strive to reduce the core temperature by the necessary 5% so that you could suppress the boron-8 flux that was dominating the chlorine rate. Some of the more interesting ideas focus on physics assumptions of the standard solar model. One was the homogeneity of the sun. There were discussions about whether the sun could have passed through a dust cloud or been influenced by the infall of planets, so that the metallicity that we deduce from the surface does not really reflect the interior metallicity. There were issues concerning the sun's 1D character. We only solved these equations in one dimension. And perhaps the earliest idea of this sort was by Esser and Cameron, of core mixing that would replenish the core hydrogen. So that's both lowering the core temperature and reducing the long-term luminosity growth of the standard solar model. So helium-4 would be washed out to larger radii, and fresh proton would be washed into the core. And then there were ideas, and I think the cleverest of all was the solar spoon by Dilke and Goff, that would relax the assumption of hydrostatic equilibrium. The last idea of the solar spoon is particularly amusing, so I'll just show you how that argument went. So Dilke and Goff are interested in figuring out what the equilibrium abundance of helium-3 is after the peak chain has begun to burn. So at early times, it looks like what's depicted here. If you wait a little bit longer, it looks like this. A little bit longer, it looks like this. It keeps burning to its equilibrium value, but at larger radii where the temperature is colder, it takes a longer and longer time to reach that equilibrium abundance. And so you gradually build up this steeper and steeper gradient that peaks at a more and more distant distance from the core of the sun. What Dilke and Goff pointed out is we now do a little experiment. You grab a volume of that helium-3 near the peak, and you give it an impulse. You throw it toward the center of the sun. What'll happen is that mass will go into the interior where it recognizes that it's out of equilibrium. It'll burn at that higher temperature, at small r. And when it burns, it becomes buoyant. It returns back to the point where it was thrown. And if you measure the kinetic energy of that volume element at that point, you find out you have more energy now than you gave it with the initial impulse. So this is the description of overstability in a star. And the existence of this overstability was actually verified by several other solar modelers at the time. The issue was what this overstability would do. Dilke and Goff postulated that this would be sufficient to cause an overturn of the sun. And so the time period it took for this composition gradient to grow was about 300 million years. So once every 300 million years, you'd go through this episodic cycle where there'd be, because of this instability, there would be a sudden mixing of the core. After that mixing relaxed, takes about 2 million years, something comparable to the Kelvin time of the sun. After that disturbance relaxes, the sun burns at a cooler stage for a while, recovers the equilibrium, and then acts as a normal sun for another 300 million years. The issue of this was whether this kind of instability would actually cause overturn or not. And eventually, and it was actually determined empirically, but eventually the consensus was that this might cause some finite amplitude oscillation of the matter, but would not cause convective overturn. And this came about because basically empirical tests of these ideas became available. So it wasn't just a matter of theory, but you could actually look to experiment to find out what was viable or not. And these were two, helioseismology and neutrino measurements. The helioseismology, mixing models like the solar spoon, if they're triggered by this helium-3 mixing, of course, during the mixing, it would necessarily change the helium-4 profile as well. And this would alter the sound speed in a characteristic way and have an influence on the helioseismology. The first people to actually think about these constraints were Christian Dalsgaard and Goff in 1976. They used individual modes, helioseismic modes, to constrain the solar model. At that time, the data were such that both a low helium abundance, that would be a mixed sun, and a high helium abundance solutions were still viable. But by 1983, the data and the inversion methods had improved to the point that only a high Y solution was viable. So this would rule out models like the solar spoon and many other that caused core mixing. And there continued to be, until today, constant improvement in the helioseismology from the various experimental efforts that have been mounted, observational methods that have been used, and ultimately yielding understanding of the sound speed at the order of 0.5%. The other new constraint on these non-standard models were, of course, the information coming from neutrino experiments, and most especially the gallium experiments. The gallium experiments, initially, it was there was an international effort to realize a gallium experiment. It was organized in 1978, and it involved Accademia National Laboratory, the Institute for Advanced Study, MPI, Heidelberg, University of Pennsylvania, and the Weizmann Institute. The experiment was envisioned as a 50-ton experiment, be co-sponsored by the US and by Germany, 50 tons to measure the low-energy PP neutrinos. 1.3-ton pilot experiment was done at Brookhaven, demonstrated quantitative extraction of the produced germanium from the gallium chloride. The efficient counting of germanium by its electron capture was demonstrated at MPI. So basically one had in place very early the demonstration that this experiment could be done. And in the US, despite the endorsements of two very high-level review panels, US funding never came. And so this delayed this really important experiment for something on the order of 6 to 7 years. Finally, the effort was reorganized in Europe with the necessary international agreements for gallium procurement quickly going forward, leading to Gallex at Gran Sasso. And a parallel effort in the Soviet Union also began using gallium metal, the SAGE experiment at Baksan. So these experiments are important because they have sensitivity to the full spectrum of solar neutrinos, including the PP neutrinos. And the most important distinguishing aspect of this experiment in terms of its relevance to solar models is that it had the potential to distinguish at the time between astrophysical and particle physics solutions to the solar neutrino problem. There was a minimum astrophysical counting rate for this experiment of about 79 SNU, if we assume that the weak interaction physics was that of the standard model. And this corresponds to the sun producing all of its energy through the PP1 cycle, producing just PP and PEP neutrinos, and again, assuming a steady state sun. In combination with results from the chlorine and expected from Kamioka 2 was also recognized that gallium measurements would factor possible oscillation solutions, so solutions that did invoke new physics, into islands in the delta n squared sine squared 2 theta plane. So these later became known as the LMA, SMA, and low solutions, MSW solutions to the solar neutrino puzzle. The results from the Gallex, GNO, and STAGE experiments proved near the minimum astronomical value after many years of measurement. So it was in marginal conflict about 2 sigma with that minimum astrophysical bounds. But that had even more impact at the time were the results of combining the gallium, the chlorine results, and the new results that also emerged about the same period from Kamioka 2. There are various authors that have tried to summarize the results here, but I like in particular this graph that came from Hatta. What is shown here is a function, is a plot of the beryllium-7 flux normalized to its standard solar model value versus the boron-8 flux normalized to its standard model value. And what you see, and at the very top right-hand corner, you see a bunch of dots, and those correspond to the standard model, standard solar model, where the various input parameters are Monte Carlo. And in addition, various non-standard models are introduced, including exotic things like production of weakly interactive massive particles that transport energy, or radical changes in S factors. radical changes in the heavy element abundance. And what you see, regardless of what you do, whether it's within the context of the standard solar model or involves some non-standard model, that there's a characteristic profile of the ratio of beryllium-7 to boron-8 neutrinos. And it follows this power law, which just says that the really only important thing for determining the neutrino flux is what the core temperature winds up being. So that becomes the one parameter that is important that you extract from all these models, whether they're the standard model or whether there's some variation thereof. And what you see is that data, when you combine these three experiments, we're far from that line. So that made it very implausible. The combination of this plus the tension with the minimum astronomical value made a lot of people begin to think that the possibility of a particle physics solution to the solar model was a lot higher than folks had initially believed. And so that, in a way, set the stage and gave the impetus for the new generation of large direct counting experiments that we benefited from, Supercommuto, Quanta, Borexino, excuse me, and Snow. And today we've already heard about Borexino's impact on neutrino physics, and of course the particle physics aspects are spectacular. First, the mapping out of the transition from vacuum-dominated to matter-dominated oscillations, and the fact that we were able to use this experiment to actually determine the ordering of two of the mass eigenstates, something we're trying to repeat today in long baseline experiments for the other neutrino pair. But Borexino also provided pioneering tests of two of the most important questions we can ask about our rather simple standard solar model, which is really, it was also the foundation of our understanding of basic sequence stars generally. The first is the equivalence of the sun's electromagnetic photon and weak neutrino luminosities. This test is the experimental test of the assumption of a steady state nuclear burning in the sun. And it's important to the arguments that use this equivalent. It is important to arguments that use this equivalence to constrain additional physics that might come from beyond the standard model, like the emission from the sun of some undiscovered light particle. Second is the assumption that the sun was homogeneous when it was formed. Let's test our understanding really of our early solar system, and thus the evolving, and it turns out the evolving exoplanetary system generally. I'll try to touch on both of these statements in a moment here. This latter question is connected to the solar abundance problem, and the measurements of the sun's measurement of the sun on the surface and in the core are not in good agreement. In the photosphere, with the recent examination of photo absorption lines, gives a lower metallicity than one deduces it from the interior radiative zone based on helioseismology. And until very recently, the answers differed by about 25%. So these are known as the GS98 and AGS-S09 high Z and low Z standard model. And their comparisons, their predictions for solar neutrinos are shown there. And it can be seen that the neutrino results sit roughly in between and are not accurate enough to decide the issue of whether our sun is a high Z or a low Z standard solar model. These changes came about because about 15 years ago, the MPI group, Munich group, tried to build a more realistic model of the photosphere. Not because the data themselves, the photo absorption line data changed. Originally, the analysis had been done with 1D modeling without stratification, velocities, or inhomogeneities. And the MPI group, Munich group, tried to improve all of this by building basically a parameter-free 3D modeling to take into account all of this multi-dimensional physics. And there was an issue that came up immediately because although there was a lot of empirical evidence that the improvements that they made actually did improve our understanding of the photo absorption lines, the line shapes, the agreements of a given line when measured in a molecule or atom, a lot of things improved, became more consistent, and yet there emerged immediately in the context of the standard solar model discrepancy in the interior of helioseismology. The helioseismology now began to diverge from its deduced values by significantly more than the error bars. And if one looked also not just at the radiative zone, but at the convective zone, the parameters of the convective zone also deteriorated with the low Z model, with the convective zone having too little helium and having a radius that differed from the deduced value. So so the abundance extraction as well as the tension with helioseismology, though, is coupled to other standard solar models. One is that the other standard solar model uncertainties. One is that the variations in abundances are really not distinguishable from variations in atomic capacity profiles. And so it's a couple of nice papers by Belanti and Serenelli addressing this. So one needs additional observations to break this degeneracy, to distinguish something that comes from a change in the metallicity from something that changes the opacity. This has actually been underscored in a recent re-examination of the photospheric results by Mogg et al. That combined a bunch of improvements. One was new observational data, non-equilibrium modeling of the photosphere, as it should be done, new oscillator parameters that affected opacities, and new oxygen and neon abundances. This led to a revised photospheric abundance that treated the photosphere in a realistic way, but at a much higher metallicity, much closer to the older values. So my perspective on this is not so much the debate between a low Z or a high Z model, but the fact that neutrinos are really interesting. This question is fundamental to the standard solar model. Is the sun initially homogeneous? Is the surface of the sun and the core of the sun linked in some quantitative way in the standard solar model? And can we verify that in the standard solar model by doing an experiment? That's what we should be doing to test the standard solar model. And this is associated with the beginning of this talk, where I pointed out that the Higashi phase argument was the original justification for assuming a homogeneous sun. Is that really convincing in view of the fact that lots of things happened after the Higashi phase, including the formation of the planetary disk? So one of the things we've learned in the last 20 years is about the abundances of metal in the gaseous giants. So this is data from the Galileo mission, and you see that the composition in elements like neon and carbon, nitrogen and carbon, are something on the order of 4 to 8 times enhanced relative to those of the sun. So it tells you that the evolution of planets in a protoplanetary disk was complicated chemically because there was a lot of sequestrian metals in the planets during the formation time, which is usually estimated to be on the order of 1 million years. So this is kind of a cartoon of the way we view protoplanetary systems. So this is a picture, say, of our sun at the point that it's sort of 95% formed. Most of the angular momentum in the disk in the original system is now concentrated in the disk. The disk has formed into a broad plane. In the middle of that plane, in the dead zone of that disk, is where the ice and dust accumulates and where the planets form. And what happens is, as the planets move within that midplane, as they lose energy and drop toward the sun, they can absorb a lot of the ice and dust, build their masses, and sweep out from that gas a lot of the existing metals. The result is that what gets secreted onto the sun is much purer gas phase than the gas that was originally in the primordial gas ball that did collapse and form the planets. And in fact, Jupiter's composition is consistent with a scenario where 2/3 of the hydrogen and helium that initially belonged to Jupiter was lost to the sun. It's lost to the sun because at that radius, that gas is still gravitationally bound. And in fact, we see evidence for this today directly, visibly in early young solar-like systems. There was a recent analysis of the inner disks of 26 T-Tauri stars. So with planets, these are planetary disks. These are star systems like our early sun, where very large depletions of carbon were systematically seen through all of the samples. with some of them being extreme, factors of 40 or so from the initial value. So what was imaged was the gas that was accreting onto the star relative to the protoplanetary disk. And this is consistent with theory. If in the best dynamical models today of the disappearance of elements from the gas phase, species such as carbon monoxide and CH4 are always significantly depleted. So one could reasonably conclude at the late stage of solar formation that something on the order of 50 to 90 Earth masses of metal was scrubbed from the gas cloud, and the depleted helium and hydrogen and helium remained in the solar system and therefore likely accreted onto the sun. A more difficult question to answer is, does this appreciably alter the solar structure in any way? And possibly yes, if that gas were deposited when the sun had, late in the sun's history, when the sun had a modern convective zone. That's something after the 30 million years after the late in the 30 million year period where the convective zone was evolved. And no, if it were accreted at earlier times when the evolving convective zone contained much more than 2% of the solar mass. And one of Borexino's last achievements was to demonstrate that the sun's core metallicity could be measured directly, free from all other standard solar model uncertainties like opacity. And that's a wonderful fundamental measurement for the standard solar model, to be able to measure directly the core metallicity and compare that to the surface metallicity that we can get from photoabsorption line to address this issue experimentally. Are the two metallicities in agreement when you take into account very small corrections due to things like diffusion? And there's an argument for how to do this that Aldo Serenelli and I worked out some years ago, and it's kind of cute. It involves a proportionality between the CNO cycle neutrinos, here in this case oxygen-15, and those from boron-8. And the boron-8 is interesting in this context because the boron-8 is a thermometer and takes into account the temperature dependence of the boron-8 neutrinos. The CNO cycle has that same temperature dependence as the scaled boron-8 neutrino flux rate. In addition, it has an additional linear dependence on metallicity because it's catalyzed by carbon and nitrogen in the core of the sun. So the result is X, which is the amount of carbon and nitrogen in the core of the sun, can be measured to almost independent of solar model uncertainties by forming these two ratios and deriving what the additional value of X might be. So this uses the boron-8 flux as a thermometer, and then removes all of the TC dependence in our predictions of solar neutrinos. And in fact, on the right, there's a graph showing as a function of Monte Carlo in the standard solar model that there's this beautiful correlation between these two ratios. Borexino's final results were announced just this past summer in exploiting their directional method, and gave a surprisingly accurate value for the CNO flux, an uncertainty of something on the order of 20%. It's actually in very good agreement with the high Z standard solar model and in tension with the low Z model. So consistent with Mog's recent analysis, which is really satisfying. But I would stress that this is much more than just adjudicating a standard solar model dispute. This gas that they're probing in the center of the sun is the most pristine sample of the primordial gas cloud isolated in our solar system. It's the first gas that was actually chemically sequestered from the rest of the solar system. As soon as that radiation core began to form early in the sun's evolution, that the gas no longer mixed with its environment. So if you want to go to any place in our solar system to learn about the nature of the primordial gas cloud, you go to the very core of the sun. So Borexino directly determines the Z of that gas, and it's in principle a measurement that's subject only to minor metal diffusion uncertainty. So it's really fundamental. Finally, let me just conclude with one more thing that Borexino and Gallex have both been very important to, and that's testing the second fundamental assumption of the standard solar model, that the sun indeed burns in hydrostatic equilibrium, driving its energy from hydrogen burning. This assumption implies an equivalence between the sun's weak and electromagnetic luminosities that have been studied by a number of authors. And it basically allows you to, if you can measure the solar neutrino fluxes and measure the photon luminosity, you can form equivalence between the two that should be satisfied if this condition holds. So this gives us an experimental test of this fundamental standard solar model assumption. The fractional error on the photon side, the right-hand side of this is less than 1%, so on the order of less than 0.5%, but on the right side is almost 10%. The error budget for the left side includes uncertainties in the neutrino mixing and in the PP2 and PP3 neutrino branches, but most of the uncertainty comes from uncertainties in the PP and PEP fluxes. And these are the fluxes that tell us the rate at which protons are being consumed in the sun. And what we know about these fluxes today come entirely from the combined gallium experiments and the Borexino experiments. And although both have significant errors, something on the order of 10 to 12%, they're in remarkably good agreement. But much more is needed. So this is one example, despite all that's been accomplished in the last 40 years in solar neutrino physics, where our field really has something more to do. Until our field measures this flux to about 1%, that uncertainty is defined by the fact that we can calculate the S factor for proton PP burning to about 1%. We will not have really exploited this powerful experimental test of the standard solar model. So there's more left to be done with solar neutrinos. So I want to stop here now. But I want to say first, my sincere congratulations to the Gallex and Borexino collaborations for helping make neutrino physics, solar neutrino physics, into one of the great discovery stories of modern physics. I'd also like to thank Gran Sasso for the consistent support they provided to enable this science. And I want to thank my many friends in experiment and theory who have always made it a pleasure to work on solar neutrinos. I think their enthusiasm for the field and camaraderie have really been and continue to be quite special in physics. Thank you.
Thank you for very comprehensive and clear presentation. And I would like to ask if there are questions or comments in the room. Okay, there is one. That doesn't work, probably the microphone.
Can you hear me? Yeah, this time, yes. So thanks for a nice talk. I would like to ask some more details or clarification about the hypothesis that originally the cloud within the solar system from which the sun was created was not homogeneous. Like we have the plots which show the correlation between the isotopic ratios in the C1 carbonaceous chondrites and the photosphere that are fully correlated. So, yeah, isn't this in the contradiction with what you discussed, that the cloud was not homogeneous?
So I think the original argument from using the Hayashi phase was that even if the cloud were inhomogeneous initially, that possibly affected by whatever generated the collapse, that inhomogeneity would not have survived because of the fact that the gas cloud goes through a convective phase before the sun is created. And the issue from that is the fact that that's actually true, that you would start with a homogeneous gas cloud. So this would come to the question of exactly when do what kinds of events occur after that point. But what's clear after that point is that there's a large amount of metal segregated in the protoplanetary disk, something on the order of 50 to 90 solar masses. And that's just by measuring the metallicities in the gaseous giants and deducing from that how much extra metal is in there. The question is now, so we know that there has been some chemical differentiation due to planetary formation. The question is it significant enough to cause any impact on the sun? one way to compare what is 50 to 90 Earth masses of metal, what does that correspond to in the sun? It's roughly 30 to 40% of the metal content of the modern convective zone. So if the depleted gas were somehow accreted onto the sun when it had a modern convective zone, it would have a substantial impact in diluting the convective zone. But if it depends on the time at which this physics actually occurred. That convective zone didn't reach its modern form until roughly 30 million years after the zero age main sequence began. And so if that gas were accreted earlier, it would have a much, much smaller effect because it would be diluted by a much larger mass. So those are possibilities. What constraints exist on this? Well, I think one can debate, but I think what's clear is that what you should actually do is do a measurement of the quantitative measurement of the core metallicity, so you don't have to worry about subtracting that core metallicity from helioseismology, where there are degeneracies associated with descriptions of opacities and so forth. And that can be done by Borexino. That's what I think is their great achievement. And they have a direct way of measuring the core metallicity.
Okay, thanks. Other comment or questions? Okay, so thank you very much for your, and thank you again. So for the concluding remark, I ask Lucia to come here with me, and I left her the conclusion of this meeting. Okay, the slides.
And I'm happy to have the opportunity to celebrate two important experiments performed at Gran Sasso that marked the history of the solar and neutrino physics. It's well known that the sun is the source of the energy that allowed the birth of life on the Earth. On the top of the atmosphere, we receive a very huge amount of power in the form of radiation at 57,000 Kelvin. And life on the Earth depends on the balance between the power received, emitted, re-emitted, reflected, or absorbed. So the studies on this delicate equilibrium are at the basis of the ecology science, and scientists have been warning us for a few decades about the anthropic effects that is altering too quickly. Non vorrei... Dov'è il computer? Perché forse bisogna tenerlo sul computer. So I will continue. The human being had always wondered about the nature of the... so this is the highlights of my talk, but we can go on. So about the nature of the sun, but still in the 19th century, still the question was, how does the sun shine? And related to this question, what is the age of the sun and of the Earth planet? If the source of the energy had been the chemical combustion, the sun would have been not more than a few thousand years. If the source had been the conversion of the burning gravitational energy, only a few millions years. The theory of the stellar nucleosynthesis that is at the basis of our present knowledge of the functioning of the star was established just before the Second World War, mainly by Hans Bethe, who developed a model that which, with some changes, obviously still valid today. The sun was found by a huge cloud of hydrogen containing some helium. Gravity compressed this cloud up to values of temperature and pressure sufficient to trigger diffusion nuclear reactions, transforming essentially four nuclei of hydrogen in one nucleus of helium, releasing of the order of 27 MV. The so-called standard solar model that we heard today many times has been developed by John Bacall and collaborators progressively, and all the available data at the time were combined in order to predict the total flux of the neutrino that must be produced in the fusion reaction. So at that moment, it was clear that the key for verifying the sun and star functioning was the detection of the neutrino, solar neutrino. Years before, in the 40s, Pontecorvo already suggested to use nuclear transition in order to measure this neutrino in a radiochemical experiment, and in particular he proposed the transition then used at home stake. But we had to, as you know very well, we have to wait up to the 60s, early 70s in order to see this radiochemical experiment fully carried out at home stake. In the standard, in the reaction of fusion of occurring in the sun, are produced not only neutrinos, but photons, positrons, and so on, but only a neutrino can escape from the sun's core and reach the Earth in about 8 minutes. All the reactions, or better, 99% of the solar energy is produced in a group of reactions grouped in the so-called proton chain. 5 of these reactions of the PP chain produce neutrino, while only about 1% in the sun is produced through the CNO cycle. You know already all this. The CNO cycle is obviously more important, not so obvious, is more important for massive star than the sun. The standard solar model not only predicts the total flux of a neutrino, but also the energy spectrum is the famous solar neutrino flux that you can see here. As I already said, the Ray Davis pioneering experiment was performed at home stake in a mine starting from the 70s of last century. It was a radiochemical experiment measuring just the transition between chlorine and argon-37, followed by the extraction and capture of the few atoms of argon in a gas counter, where these radioisotope atoms were counted. So this was the first demonstration of this technique. capable to extract very few atoms out of tons of target material. The threshold of the reaction was 0.8 MeV, so the experiment was only sensible to beryllium-8 and beryllium-7 neutrinos. Unfortunately, Ray Davis didn't succeed to use a calibration source at that time. As well known, the big surprise was that the experiment measured only about 1/3 of the expected solar neutrino flux. At that moment, possible reason for the deficit could have been both the solar model was incorrect or the experiments. And this is the beginning of the solar neutrino problem that was a real puzzle whose design only revealed completely when many tiles were inserted. A further tile on the solar neutrino puzzle was added in 1987 by the Kamiokande experiment in Japan, followed by Super Kamiokande. Kamiokande was a water Cherenkov detector measuring in real time the upper part of the boron-8 neutrinos through the neutrino electron scattering. So there was a correlation between the direction of neutrino and that of the electrons, and this is important in order to verify that the detected neutrinos are coming from the sun. Obviously, the deficit, the confirmation of the boron-8 deficit observed in the home stake stimulated a variety of different theoretical efforts in many directions in the solar model, nuclear physics, and particle physics, including the hypothesis of the electron-neutrino disappearance along the path from the sun to the Earth. Even earlier, starting from an idea of Pontecorvo in the 60s, the theory of neutrino flavor oscillation, and together, time different, but together with the enhanced oscillation in matter, have already been postulated. So, in the early 90s, it became clear that in order to solve the puzzle, possibly ruling out the astrophysical solution, it was necessary to measure the bulk, the most abundant solar neutrino, the PP neutrinos of the PP chain, more directly connected with the well-known solar luminosity. Obviously, this demanded a detection reaction much lower, less than 420 keV, and a very low background experiment. The only solution was to use the gallium-71, germanium-71 reaction, and at that time, two experiments started more or less at the same time: SAGE at Baksan in Russia, and the Gallex experiment at the Gran Sasso. So this is the moment when the Gran Sasso entered the game. We heard also from Professor Maiani about the beginnings of the laboratory, but I would like to underline that 40 years later than its conception, the lab is still the largest, I think, not Jinping still, is the largest and the most advanced infrastructure for astroparticle physics. And that the astroparticle physics would not be been able to have this rapid progress without this infrastructure, the underground laboratory. So having conceived and built such a large, well-equipped lab as early as the end of the 70s, allowed Italy to grow a great expertise on this sector and take a leading role that it still holds. You know very well, most of you know very well the laboratory, 3 huge halls for a total surface of 18,000 square meters, and outside the laboratory. And I would like to note that the Gran Sasso Lab is run as an international science facility, as the experiment must be approved in advance, not only by the INFN, but by the International Scientific Committee. All the past and present experiments at Gran Sasso are trying to look at fundamental questions like what is the universe made of, what is the intimate nature of neutrino, what we know about the sun and all the other stars interior. So the main research activity of the lab can be grouped in neutrino physics, search for dark matter, and nuclear astrophysics. In this sector, the Gran Sasso has a long tradition, first with the Luna, and now with the Luna Megavolt, measuring cross-section of relevant reactions occurring in the stars, both in the PP and CNO cycles, accessible, measurable only underground. And then there is other experiment on associated science, geophysics, and biology. For what concerns the neutrino physics, we can group in solar neutrino, atmospheric neutrino disappearance, and tau appearance oscillation, as Maiani mentioned with the CNGS cell to neutrino Gran Sasso beam, search for neutrino from collapsing star, and nowadays the focus of the laboratory is mostly on the search for neutrino-less double beta decay with more than one experiment, at least 3. At least the 3 that is, as well known, is the only way to verify the Majorana nature of neutrino. Obviously, I cannot mention all the experiments, past and present, of the Gran Sasso Laboratory, but I want to stress that all the experiments were or are at the cutting edge of the knowledge and reached the world record in sensitivity. I found this old picture dating back, I think, to the 80s, if I remember well. You can recognize a few Nobel Prize and very eminent scientists, protagonists of the scientific life of the laboratory. And unfortunately, we note that some of them has already been recalled, passed away, and I want to express once again my regrets. So coming back to the solar neutrino physics, we heard already from Professor Kirsten all the details containing the Gallex GNO experiments, but just to summarize, obviously it was the first solar neutrino experiment at the Gran Sasso. Was a radiochemical experiment measuring the solar neutrino through the gallium-germanium reaction. The main characteristic of this experiment was that they aimed to measure the bulk of the neutrino, so the PP neutrino. The threshold then was 233 keV, so all the PP neutrino were measured, and in total 92% of the solar neutrino facts. It was a very challenging experiment in terms of target radio purity, separation of germanium, a few atoms of germanium from gallium at the level of 10 to the 30, the low level proportional counting and so on. Important point that the reliability of this radiochemical experiment was tested through the use of huge neutrino source chromium-51. So, as you heard already, that the first results on the detection of PP neutrino were announced in '92 in Neutrino in Granada, up to 1897 when Gallex stopped the experiments confirmed the presence of PP neutrino and a significant deficit of the sub-MeV solar neutrino. So that means that this was the first strong experimental demonstration of the nuclear fusion process in the Sun. And as already was quoted, the strongest indication at the time of neutrino oscillations as a solution of the solar neutrino puzzle. The following GNO experiment measurements improved the quality of the data, added the restriction on possible time variations, reduced the total error on charge current reaction rate, and a more recent analysis produced updated results, including a new evaluation of the PE survival probability only of PP neutrino, so after the subtraction of the contribution from boronate from SNO and Super K data, and of the beryllium-7 contribution from Borexino. So without this radiochemical experiment, the largest fraction of solar neutrino flux would have been remained undetected. So in a sense, we could say that Gallex placed a tile on the puzzle of such importance that we could glimpse the design of the puzzles. And Morales at that time said, also Kirsten quoted this, the first Gallex results marked a cornerstone in neutrino history. The decisive and final proof that the source of the solar neutrino problems lay in the oscillation of electron neutrino in mu and tau neutrino were given by SNO in Ontario, in a mine in Ontario, in Canada. SNO was a real-time Cherenkov detector filled with heavy water, surrounded by normal water as a shield, eventually with improved neutrino capture capability using some additional salt. Using heavy water, SNO was able to measure two separate reactions, charge current interaction sensitive only to electron neutrino, neutral current interaction sensitive to all flavors neutrino, and moreover they measured all flavor neutrino to the neutrino electron scattering. It's well known that the results was that the total flux was in agreement with the standard Söder model, and electron neutrino was about only the order of 30%. So this was a clear demonstration that the electron neutrino along the path to the Earth changed their flavor. This was the only model-independent measurements of the total solar neutrino flux, but we have to recall that SNO could measure only the high tail energy of the boronate neutrino corresponding to 1% of the total flux, neutrino flux. So at the beginning of the new millennium, despite great achievements on the solution of solar neutrino problem, a complete, precise spectroscopy of the different process of the PP chain was still missing. As early as the 90s, as Professor Bellini said, the Borexino collaboration proposed an experiment at Gran Sasso just with the purpose of measuring in real time and separately the different flux of the different neutrino of the solar neutrino energy spectrum. Finally, the experiment took data from 2007 up to 2021 at Gran Sasso. You heard already the detail of the experiment, so I don't go in details. Is a liquid scintillator detector with an onion-like structure with radio purity increasing towards the center. But the main characteristic and the key for the success of Borexino were the unprecedented levels of radio purity and extensive thermal stabilizations. So this world record in a sense reached are well beyond the first hope of the collaboration and are the key of the full success of these experiments. Neutrino of all flavors were detected via the elastic scattering and antineutrino via the inverse beta decay. So I only listed here, summarize the main physics reach of this unique experiment. Borexino was the only experiment that has performed the full spectroscopy of the PP chain, having measured the PP, beryllium, PEP, boronate, neutrino, and provided the first ever measurement of the CNO solar neutrino with a large confidence level. Moreover, the experiment was able to test simultaneous flavor conversion both in the vacuum and in the matter-dominated regime. And you heard that the transition region is important in order also to search for non-standard neutrino interaction pointing to physics beyond the standard model. The analysis of the flux of beryllium-7 and boronate, and mainly the CNO flux, resulted in favor of the high metallicity standard solar model. Obviously, the standard solar model depends on the abundance of elements heavier than helium, the so-called metal, as they influence the opacity and the temperature and then the rates of the reactions. The CNO measurements are more directly connected with the metallicity of the sun, and what is important to underline is the fact that the sun's metallicity keeps memory of the primordial composition of the sun, so the measurements of CNO neutrino is a unique probe to test the primordial compositions. Neutrino also measured the expected seasonal modulation of the beryllium-7, and also important is the fact that for the use of beryllium-7 and CNO measurements, they use the so-called correlated and integrated directionality technique based on the combination of both Cherenkov and scintillation signals. So Borexino not only paved the way to next generation liquid scintillator detector, but also to hybrid experiments. They also provide a limit on neutrino magnetic moment, but just a mention also of the measurements, very important measurements of geoneutrino. So what will be the future of solar neutrino physics? Solar neutrino physics certainly has given a fundamental contribution both to astrophysics, testing the solar stars model, but also to particle physics through the discovery of electron-neutrino oscillation and neutrino mass. Combining the results from the solar neutrino experiment and from reactor experiment, mainly Camland, the large mixing angle solution was established as the correct set of missing parameter. In particular, the order of one of the pairs of neutrino of defined mass has been established. But still, there are several key aspects on solar neutrino, as we heard today, that require further clarification. Fortunately enough, there are already next generation experiments pointing or to larger scale or cleanness or depth that are in different phase or in construction or planned or proposed. We heard many detailed discussion about the still open problems of solar neutrino. I listed here very briefly. There is still space and need for improved determination of the parameters, since still there is a small tension between reactor and solar data, unless new news are maybe are coming. As I heard already, to solve the question of the sun's metallicity is a relevant topic, and neoneutrino are a unique opportunity in this regard. There is still space for non-standard interactions, studying transition region, the night asymmetry, or also search for antineutrinos, but also a detailed analysis of the energy dependence in the low energy region can put tight limits on the origin of the solar energy and on non-standard energy channels. Still, the HP neutrino are still missing, also if they contribute only to 10 to the minus 5 are the total solar flux. And there is also interest in search for action, or more general action-like particles, as they could be good candidate of dark matter. From the experimental point of view, there are no at the moment single purpose on solar neutrino planned, so the tendency is to exploit the characteristics of the multi-purpose detectors. I put here a plot, a kind of a plot from this reference where they tried, the authors tried to summarize the main characteristics and physics reach of different kind of detectors. For what concerns water Cherenkov detector, Super K is still running, while the excavation for the site of Hyper K has already started. The liquid in the liquid scintillator detector, surely Juno and Snow Plus are quite relevant experiment, and I would like to stress that Juno, in a sense, benefited from the great and successful inheritance of Borexino. The experiment is in an advanced phase of construction phase, and we are confident that next year it will start to take data. Then there are also ideas concerning the use of different species of hybrid detector in Jinping, EMI Lab, Jinping in China, EMI Lab in Korea, TEA is a program in the US, but also noble liquid detectors, including those for the search of dark matter, could address the measurements of solar neutrino. So I arrive to in my conclusion. The present status of the art is that despite the great progress, some of the main neutrino characteristics remain unknown, like the neutrino mass and hierarchy, and whether the neutrino is its own antiparticle. There is space and need for improvements both in the solar knowledge and in particle physics through the solar neutrino studies. So solar neutrino physics still remains a frontier research topic, and from all the talks of today, I think that the general conclusion is that Gallex, Gignot, and Borexino experiment have marked the history of the neutrino physics and of the Gran Sasso Laboratory. Thank you.
So, thank you, Lucia. Question or comment? So, I have a comment. You said that the Gran Sasso is the reference laboratory in the world, and at the moment I would like to say that the Gran Sasso is in a very good shape, in a sense that I think that the Gran Sasso remained the reference in the research of the underground all around the world. The competition is not at the same level as respect to many years ago, but in few years we will have all around the world something around 15 underground laboratory, and some of them will be larger with respect to the Gran Sasso and deeper with respect to the Gran Sasso. But for the moment, I think that the Gran Sasso have a very good reputation that was done thanks to this very important experiment performed in the past, thanks to the director like you, like Stefano, and like the other. The present director, the only thing that I have done is to close Borexino. That is not that is not a good thing for my career, for my curricula.
Health,
that is
your
not.
health.
Yes, it's so you can complain with me because I'm not so the remarks of the research activity. So I think that the strategy of the INFN and the director, I would like to stress this point. Pointed out that the investment done in the Gran Sasso Laboratory and the investment done on the experiment in Gran Sasso was successful, and I hope that in the future we will be able to support again frontier experiment also for new physics. So that's thank you for the support, and thank you for your activity. And so
I fully agree, obviously, with your comment, because it's not a question of dimensions or even a number of experiments, but as I said, there is a long tradition in astroparticle physics in Italy because of the Gran Sasso Laboratory. So this is the higher value of our community.
Okay, if there are no other questions, I would like to thank all the speakers first, and Lucia at the end. I would like to thank all of you that you participate to this event. I thank Gioacchino, that was the more important person that helped to organize this meeting. This was, in my opinion, was a very beautiful meeting, and I have the possibility to see what happened in a relatively long time, starting from 30 years ago at least. That is important, in my opinion, because what we learn is important also for the future. So I hope that it was, I think, I'm convinced that it was a very good occasion to renew what was the important result obtained by the Gallex and Borexino experiment on solar physics. Okay.